watch on the YouTube live stream. I will start a screen share with the general program. Here we go. And then we'll wait 2 minutes for everyone to arrive and get started. Hello, everyone. Great you're coming in for today's special session. We will take 1-2 more minutes for everyone to arrive, and then we will get started. In the meantime, give some music recommendations so we can do that the next time, so we have some waiting time. Would love to include all the recommendations from all over the world. It's great to see that people are already starting on the Global Quantum Project. Tomorrow we will do a Q&A about the projects and you will get some more instructions. And then we are starting a really exciting week now. First with a special session with David DiVincenzo, then more about neutral atom quantum computing. Tomorrow, a session on this, how to really program a neutral atom quantum computer. I will keep talking a little bit until everyone is in and then start the official kickoff of this session. 160 people already coming in. Wonderful. The YouTube recordings have also been viewed really a lot. It is great how many quizzes everyone already finished for Q Bronze, Q Nickel, and that really paves the way for this week's program. And this week will be the first week that we will have more about hardware, that we will see the virtual lab tours, see what is really going on inside a quantum computer. It's too fast. Let's get started. Hi, everyone. Great you're here. Happy that everyone is coming for today's special session with David DiVincenzo. We will start with David DiVincenzo's keynote on quantum computing, about which we're all very excited. And then afterwards, we have a hardware lecture on neutral atom quantum computing by Jeff Thompson today. This will then lead us smoothly into the introduction to quantum computing with neutral atoms tomorrow by Pedro Lopez from Quera, which is a software bootcamp where you can really do hands-on work. We are currently also live on YouTube, and you can invite all your friends to watch there and see this special session. I would like to give a warm welcome to Dr. David DiVincenzo. David DiVincenzo is the director of the Institute of Theoretical Nanoelectronics at the Peter Grunberg Institute in Jülich in Germany, professor at RWTH Aachen, Germany, professor at TU Delft, Netherlands, and staff member at QTech in the Netherlands. Many of you know his name from the DiVincenzo criteria, the necessary criteria for a quantum computer that have made great impact on the quantum computers being realized right now. He also proposed the first spin qubit quantum computer, the Los DiVincenzo quantum computer. And about all of this, you will learn a lot more today. David DiVincenzo did a postdoc at Cornell and then was a staff member at IBM for a long time until being called to Germany and becoming a director and professor there. We have the Discord open for all of your questions. David will give a lecture first, and then we will do a long Q&A session. And we are very excited for all of your questions being asked to David. David, thank you very much for being here, and we are ready to kick it off.
Okay, dank u wel, Marlou. And can you see my screen?
You can, yes.
That's very good. So I will launch right into a lecture today on quantum computing. I think that you, those of you in the audience, represent a great diversity of backgrounds. So I'm going to also hit a diversity of topics. So here's my outline for today, but I will leave plenty of time for discussion at the end. I will begin with what I consider the most essential thing to know about what is a qubit and how it is distinguished from a bit. And so that will be a a small tutorial about that. And you may wonder, what do I feature as the most important thing about a qubit? Well, you'll see it in a moment. Then I'll jump right to the present and show you maybe my favorite quantum computer of today, which may be a completely different one than the quantum computer of next year, but is worth looking at and trying to understand some of the features that have emerged. For many years, quantum computers were just a dream. And we were often criticized for saying, well, you keep saying it's 20 years from now, and then another 5 years later, you say it's 20 years from now. But now I can say, yes, in fact, we have quantum computers, but we'd like to have better ones. So when will we have a better one? Well, 20 years from now, I guess. But I think they will actually continually get better. I will spend some time digging back into the history of quantum computers, and we'll talk about the start of quantum computing, except I don't know what year to point to, so I'll point to all of them. So here's my list of my favorite years: 1960, or is it 1982, 1994, 2000, 2016. I could say 2016 is the year that IBM put its first quantum computer on the cloud. And maybe for many of you, that's the starting point. That's the one that marked the era of real quantum computers. But for me, or certainly intellectually, the ideas of quantum computers started way further back, and including many high points over the years. And somewhere in there, somewhere in my sort of historical story, I will tell you about those criteria that you heard about, and tell you what I was trying to do when I wrote down those criteria for the first time, which, well, to give you a clue, was sort of started happening already in 1994, and were sort of complete in the year 2000. But they're not maybe the most important aspect of the timeline. Okay, so now I'm going to begin with some really basic stuff. So I'm sure I'll bore some of you, but I hope that it's at least a little bit interesting and a little thought-provoking also for a few of you, even experts. So we talk about computing, and at least for the last 100 years, when we talk computing, we mostly talk about binary arithmetic, and we talk about, therefore, information represented in as one of two states of some object, call it 0 and 1. And now we recognized, although I'll point out it was not even so obvious in the timeline until rather long along the timeline, that the most essential thing that you wanted to do to introduce quantum mechanics into the story of the bit, into the fundamental information carrier of digital information processing, is promote it to an object that from which you can build a wave function. And so that if you have just a single bit, you should be able to make states which are not 0 and not 1, but which are, as we say, superpositions of those two, with some coefficients, some actually complex valued coefficients A and B. So we say that there's a physical reality to saying that a system is in a definite quantum state, but which makes it indefinite from the point of view of whether it's a 0 or a 1. And the point I will make is that with a small sort of Gedanken experiment is that it's not merely that it's sort of unknown whether it's 0 or 1. It's a much more definite state of knowledge than that. So let's do this by imagining that we're representing our physical, let's say, bit of information with whether a single particle, I do say single electron, and this is a qubit that we've thought about over the years, but do not find favorable, does not have really good characteristics, but is conceptually a perfectly good qubit, where we say the 0 and 1 of this single electron is whether it sits in the left side or the right side of a bistable potential well. As I said, there are so-called charge qubits, which still play a little bit of role, but which were long ago displaced by spin qubits as a favored single electron qubit. Okay, so, well, we do have the situation as the digital computer engineer would want it, single electron on the left, 0, single electron on the right, 1. So what about these other states, these alternative states? So the way I describe it here, and it was Deutsch who actually really articulated this very precisely. He says, to get to quantum mechanics, you have to think about first the idea of randomizing, paradoxically. And so you may want to bring the system into a situation where it is neither a 0 nor a 1, but in some sense a 50% 0 and 50% 1. And a regular computer engineer would know what this means also, because if you make a hardware random number generator, you do things exactly like what I'm describing here. That is, you have a bistable system and you put it in a condition where it doesn't know what to do. Or the way I've described it here is, suppose you started in the 0 state, but you do something to make it less definite, which is, for example, to make the barrier lower. And then you would often say, well, you make it so low that even thermal excitations will cause the system to bounce back and forth between 0 and 1. But I won't follow that track very much, but I will just say that for whatever reason, lowering the barrier will give the system some chance of departing from the 0 state and actually ending up in the 1 state. And suppose that probability of doing that is 50%. So you could say, and you do in fact say in a hardware random number generator, that that's a good way of producing a random bit. But from the point of view of quantum mechanics, is this state really random? One might ask. But now we have to indeed discuss more of the physical process that's involved in going from the 0 to the 50-50 case. And what we will say will be more specific here and say that that is going to occur because of tunneling, because of electron tunneling, and therefore because of a purely quantum mechanical phenomenon that particles can indeed penetrate through walls, can pass through regions where they're forbidden to be by the laws of classical physics. And so you can indeed lower the barrier. I show this sort of dotted version of the barrier, lower it enough so that indeed tunneling can occur, and then it can bring itself into this 50-50 state. Now, I see I already jumped into the punchline. I should have stayed on the last slide, because what's really very different about quantum mechanics is that you can prove that this 50-50 state, this apparently random state that you end up with, is actually not at all random. And you do it by performing or continuing the thought experiment in the following way. That is, you lower the barrier once, let it get into this 50-50 state. You raise the barrier again, hold it stationary for a while, then you lower it one more time. You try to make it, quote, even more random, but instead it sort of completes its quantum tunneling and it ends up definitely in the 1 state. So we say this superposition of 0 and 1 is not at all random, because I do something to it which from a classical point of view would make it even more random. But in fact, it makes it actually less random. It sort of completes a process and turns it into a 1 state. Now, this process of flipping from 0 to 1 is in Boolean logic what you call the NOT operation. And so what I've described is something which you do twice to get a NOT operation. And so we refer to this as a square root of NOT as a logic operation. And basically this, with ordinary Boolean logic, the ands and the ors of ordinary Boolean logic, is enough to give a whole new type of logic, which is the one based on quantum physics. So I featured this one particle, 1-bit superposition as the sort of key new feature. You would often say, well, but surely the new feature is entanglement. But I would say this plus ordinary computer logic inevitably gives entanglement, which is just 2-bit entanglement, or 2-bit superposition states, or more than 2 bits. So once you admit the possibility of having superpositions with this sort of deterministic character, you inevitably bring yourself into the state space of entangled states and into the rich information carrier that quantum states give you, and to the the essentially new software that it makes possible, the new instruction set that is made possible, that has, as is very famous, of course, high computational power. If we finally understand how to really harness it, but that indeed is still in the future. 20 years in the future, I don't know, but we're not really quite there yet to fully harness the capabilities of the quantum computers. But let me pass on from this very conceptual introduction, and that's all I'll say by way of sort of scientific introduction to the basics of information processing with quantum mechanics. And I want to pass immediately on to the here and now. So what does a quantum computer look like in the year 2023? Well, actually, I'm showing you a few things that were published in Popular Science in the year 2022. At this level, it's not so different. Well, I'll mention one way in which it isn't different already. So you're often, I bet that most of you have seen a picture like this, and you are told this is a quantum computer. This is, in fact, a superconducting quantum computer. But I really have to, in a sense, disappoint you in saying, basically, nothing you see in this photo is functioning quantum mechanically. Nothing, there is not a qubit in sight in this picture. And in fact, this picture, this is courtesy of IBM, is just the control apparatus, or the physical structure that is built to house the quantum computer. I'll show you in a slide or two where the quantum computer is. It's actually out of view in this picture. And most of what you see here is the hardware that's needed to, first of all, make the device very cold. When this is in operation, there's a can over it. There's a thermal insulation can, so that the interior of this structure, in particular the lower regions, can get to extremely low temperatures, less than 1 Kelvin. And then there are many, many wires going from top to bottom, and those are the ways in which signals are brought in to control the quantum computer. But you do not, in fact, see anything about the quantum computer itself, the qubits, in this view. If you step out from this view, so here's this animation is showing a few things which I'll go through as it loops through. So a quantum computer is one where you have to issue instructions to it, which are turned into actual waveforms, which were shown briefly in that little part of the picture. And the picture that I showed a moment ago was on the right. Now it's just disappeared again. But I'm sure some of these you know quite well. That is, on a regular computer, you write a set of instructions for the quantum computer, which look like just regular, instructions of regular programming language. There it is, like QC measure. It goes through some magic box, which is the dark blue part of this picture, gets turned into very precise waveforms. It's shown as these sinusoidal pictures as you see this looping by, but in fact, they're much more complex than that. They're usually highly tailored to do a specific job, to cause a particular operation, like a measure operation, to occur. And then a signal comes back out, which is in fact the answer to the question, at this moment, is the qubit a 0 or a 1? And then you do that innumerable additional times. If you're in the future, when we run, say, a factoring algorithm, there will be like 10 to the 18th such individual steps. At the moment, there are not nearly so many, but there are a multitude of steps. I want to say something about this dark blue region, that is the sort of the region where the computer instructions get turned into waveforms. These are highly important and specialized parts of this device. And they're probably the part which is kept the most secret by the companies that are doing this. So this is IBM's very fuzzy picture of the large control rack that is needed to prepare the signals that are going to go into the quantum computer. These are all electronic devices. They're regular digital or analog, actually mixture of both devices. And there are many, many channels, basically because every qubit has to get its own channel to the outside world. It is a little different in other realizations of quantum computers in that in many of the others, there will be some optics involved, so that computer instructions, that is regular CASM instructions, or some, Qiskit instructions will, from the high-level language, will be turned into optical pulses. That is not the case in this style of computer, which operates only on electrical pulses. Okay, so let me say a few more words about this computer. So finally, we pan the camera down to near the bottom, and now many, many more cables and control apparatuses and cables into these plugs. And the quantum computer is finally in this tiny little white region in the middle. So I didn't mean to advance quite so soon, but this is itself, and this is a chip, a region where the chip is mounted, where a chip is mounted. Let me just see if I can, I'm going to, on the fly, turn myself into a laser pointer. Maybe this one. Okay, so, oh, that didn't work. Never mind. Anyway, so the quantum computer is just this little region, and all this work is involved in contacting to it and sending very precise information to it, and then receiving precise information out from it. Now, a view of the chip as of 5 years ago, more than 5, maybe 7 years ago, at the beginning of the IBM cloud era, was that it looked something like this. Now, I'm not going to explain extremely much about what's on this chip. It looks like a microelectronics chip, but there are some important differences. One is that the device is way less miniaturized than a regular computer chip. That is, the working devices, the actual qubits, there are 16 of them on this, are in these little square regions, 8 of them lined up along here, and 8 of them lined up along here. And they are not so small. They're nearly a millimeter across. There is a working part. These are based on the physics of superconductivity. There is a very small working part, which involves the tunneling of superconducting electrons from one region to another. But it is fair to say that the entire structure, this entire millimeter-sized structure, is functioning as a qubit. Okay, so let me explain just a few more things about what has happened in the meantime to this in the years that it's been available. And I shouldn't overemphasize IBM here. I've used to work for IBM, but that's 13 years ago. And I admire their work, but I also admire the work of the Google company. I admire academic work at ETH in Zurich, for example. I admire, however, the ion trap work of Quantinuum, but I should be careful, because I would have to now name about 12 more to be fair. So instead, I'll be unfair and just stop there, but just to emphasize that there are many organizations that have done things of this complexity and definitely higher at this point. All of them have this situation that there's a very considerable classical infrastructure that's needed to take care of their quantum computer. And then there's always some unique central region where actual qubits live and are very carefully shepherded through their operations. So let me say, however, a few things more about where this goes. What is the idea? The idea, of course, is to have more qubits. There was an insight, and this is already 20 years old, that more or less regular arrays, but square arrays, that is, I should say, two-dimensional arrays of qubits, are actually quite powerful as an architecture for a quantum computer. That's partly because it's well adapted to the needs of quantum error correction. Sorry, this slide has too many words on it. I was not going to say most of these words, but just to say that already, now almost 15 years ago, at a cartoon level, it was sort of understood where this was going. In this cartoon, it was understood there should be some kind of qubits. It was not even specified which. The green dots in some kind of regular two-dimensional array. They need to have things that couple them to each other, and it was understood that linear resonators are a good scheme for coupling them. So that's all these sort of gray bars are things that couple nearby qubits to each other. They also also electrical structures specific to read out the qubits. That's these sort of wiggly, squiggly structures, also like you saw on the chip picture. But most scary from the point of view of those who build quantum computers is that every one of these yellow squares indicates a place where information should flow in and out from the outside world. So in this concept, basically, each qubit should have two inflow or outflow locations. And that sets a scale for the working quantum computer. Now, as I said, these inputs and outputs, they can be optical, using optical fibers, let's say, or they can be electrical cables, but they have to be something. And they have to be something very carefully engineered, very precisely engineered, with low noise in mind, with very low temperatures, very precise control. Now, where this is going, IBM says that they have indeed proceeded along over the years, and they now foresee that they could go far beyond 1,000 qubits. That's what this last but very indefinite milestone for the current years, the next few years, is that they say possibly, they say 1K, meaning beyond 1K, beyond 1,000, but also maybe up to 1M, meaning 1 million and plus beyond qubits. And they have some concept for how to do that, but well, it's rather unclear how much of that they will do in the next couple of years. But just to give you a perspective of what they've done and what other organizations have done as well, but they've been very open about it. So I think this is worth, praising, that this is about 5 years worth of advances in their chips. They, 5 years ago, they had a chip called Falcon, which now I don't remember the count of it, but you see it in the lower right here that that's something like 20-some qubits in this, according to the connectivity shown here. The year after that, they had Hummingbird, twice as big, the yellow patch here. The year after that, they had Eagle, another factor of 2 or more, actually, I guess in numbers of qubits, perhaps a factor of 4. And then the following year, they had Osprey. And now this year, as of now, they have Condor. So almost 1,000 qubits. That is the entire, background of this is the size quantum computer, the gate array quantum computer that they have now in their laboratories. Now, I understand their next step will be backwards. That is, these are impressive in the numbers of qubits they have. They're not super impressive in the quality of operations, the thing we call fidelity. And so they're going back to the drawing board and going back to smaller structures, but ones which achieve new fidelity goals, which make it possible to run longer algorithms, but also more exciting, perhaps for people like me, that it makes it possible for digital error correction to start becoming effective for these quantum computers. And we have always felt, and well, always for the last 20 years, have felt that that is the way that finally we will get to really scalable quantum computing, is to achieve the conditions where error correction is possible. And I'd say we're getting close, but it puts heavy demands on every aspect of the system to make it work extremely precisely, actually as an analog device, in order that finally digital error correction can be effectively used to make quantum computers do algorithms of essentially arbitrary depth or length, if you will, numbers of gates. Okay, so let me now step into my sort of historic mode. I started very generally, and now I talked about what's the present. Where did this all come from? So as I hinted at the beginning, I would say there were really multiple starts. Well, what everyone always says is that it started here. So here's a paper, actually it's more or less the transcript of a lecture given by Richard Feynman. Lecture was in 1981, but the published paper 1982. And sure enough, this lecture has indeed many speculations or thoughts about the possibility of a quantum computer. So one can certainly point to this and say, yes, this is where the story got started. And I will definitely acknowledge that Feynman, this was an important impetus to the field and rewards rereading. I recommend this as very interesting reading to those of you who wish to understand the basics of this subject. But I will say that this was, first of all, not actually the beginning. Here are some important long ago workers. And so I said, for example, that for me personally, the timeline begins with 1960, and this begins with Landauer, who understood some very basic things about information carriers, and in particular, how they would or would not consume energy. And it was his insights that told us that maybe we don't need a dissipative device to do computing. What I also focus here, or mention here, are the very notable contributions of scientists in the Soviet Union, and more particularly of the work of Yuri Manin. And those of you who are Russian-speaking could find some real surprise in the text that I have partially shown here. If you really want to have the page, I can send it to you. But who articulate several years before Feynman quite clearly what the point is of quantum computing, the large vector space, the possibility of controlling wave functions in that vector space. He actually had quite a cogent, abstract, but definitely cogent idea of what a quantum computer would mean. So now this work was little known outside the Russian-speaking world, but now we can see that if you really want to point to originators, that maybe one should point to Manin. On the other hand, the growth of quantum computing was not all that fast after Feynman's lecture either. That he himself did a little bit further work, and I just show a line of mathematics here to indicate that yes, he didn't merely speculate. He wrote down a few theories for what a quantum computer might be like. And those have been important. They were not revolutionary. He actually rather missed the point that quantum superposition was the essential aspect of quantum computing. So he really failed to notice that. But he did introduce ideas that led, on the one hand, to new ideas for the so-called complexity theory of quantum computing. And I definitely credit Aharonov for carrying this forward in conjunction also with Kitaev, who had many other insights into what a quantum computer could mean. But this was only many years later. That is, Feynman unfortunately passed away in the late 80s. So his last writings in this were in the mid 80s. And it was in fact many, many years until these ideas came up again and, came to the fore. Now, so indeed, I would say it took about, on my timeline, about 12 more years before really exciting things started to happen. And so I'll jump in my timeline up to this year, 1995. And at this point, in my view, things were really happening. That is, if you ask me, when did quantum computing start? It was right around this time, because this is where the rather abstract ideas of Feynman, or Manin perhaps, got turned into a set of concrete and very exciting ideas. This was among the first international conferences that took place, gatherings of people who were really primarily concerned with quantum computing. And some really exciting results were discussed at this meeting. I was there, there's the young me. but the factoring algorithm of Shor had just been discovered. And of course, I'm pointing to Shor in this picture. He's rather dim in this little side panel. But the discussion of his algorithm was certainly a large part of this meeting. But I've already mentioned the contributions of Dorit Aharonov and the beginnings of quantum complexity theory. There was Seth Lloyd, who was already speculating about using spins to make a quantum computer. I can point to, except I keep losing my pointer, here it is. There's Barbara Terhal, who introduced the thing called an entanglement witness right around that time. I dropped down to here. This is Tommaso Toffoli. Toffoli, you know, the Toffoli gate of quantum algorithms was introduced by him. And many of the co-authors, I don't know how many, but I didn't count, but there's Bennett, there's Joseph, the originators of quantum teleportation. So the, among the foundational concepts of quantum communication, was very much discussed. I think I see 2 or 3 more of the 6 authors of that paper at this picture. So this was indeed one of the high point academic research conferences of my entire career. And, many, many exciting concepts were launched at this meeting that kept us busy for many years. Now, actually, rather absent from this were people who really knew how to build quantum computers, I would say. But still, there was very much speculation at that time. And I'll take you through a few of the considerations of what was going on. That is, I would say initially, mostly from theorists. There were actually now many ideas. I mentioned Seth Lloyd, but in fact, there were many other ideas that all came to the fore within a few years. And I don't think I'll read through all of these. They include things that remain very active to this day as subjects for quantum computers: ion traps, neutral atoms, nitrogen vacancy centers, small Josephson junction devices, so superconducting devices like what I was featuring, and spins. But some of these also look not so familiar. The electrons on liquid helium has not taken flight, definitely. And let me also comment on nuclear magnetic resonance, that it leads the list, actually, because I'd say for quirky reasons, or I don't know, not absolutely the best scientific reasons, this was indeed the method that took flight very quickly, that some members of the group that I just showed you got very interested in this and felt that they could go into the laboratory and do work quite quickly to do quantum computing on the nuclear spins of molecules like this. Now, actually, the factoring of 15 came a few years later, but not many, many years later, on this precise molecule. And so that was, viewed as an important achievement. And there was a lot of attention to this. They said, oh, a simple instrument, you just make a sample, you put it in there, you measure, you don't need a lot of cables, you just need the kind of readout system that normal magnetic resonance instruments have. And definitely these things taught a lot about how quantum computing would be done. But I can say that I was, at this stage, I'll think, this is the late 1990s, I was rather resistant. I felt that this was actually not a good start to quantum computing. Maybe the important phrase is the one that I state here: not scalable. There was really no good concept for how this would ultimately be scaled. There were practitioners that thought maybe there would be, and they probably also said, well, it's not so important. We're just at the beginnings of this. Let's just try to get where we can get and see what will be next. But I was not so confident that that was a good approach. On the other hand, we had the example, let's see, let me go back, let me skip something. We had the example of ion traps already in this work, or this is 2 subjects that were scientifically very active in that time, in the 80s and 90s, and then ultimately were awarded the Nobel Prize in 2012. But they were indeed about controlling qubits in our current language. That is, in one case, controlling which energy level a beryllium ion would be in, what electronic energy level when held in a trap, or alternatively, what energy level of a Rydberg atom an atom would be in when controlled inside a cavity. So these were already known methods. And now you could say, well, were these the basis of scalable methods? In the form that they existed in the original experiments, no. But what influenced me very much was the fact that there had been actually a meeting in the preceding year. I had shown you the 1995 meeting, but there was even a meeting even smaller in 1994. And this, I would say, was the entire set of world researchers who cared in 1994 about quantum computing. It was definitely not a very large crowd. But I bring this out because this shows, in addition to some faces you would still recognize, a few that were not at the 1995 meeting, those being, if I can get my pointer to work, this is Peter Zoller, and his colleague, even less visible here, Ignacio Cirac. Now, some of you know that Cirac and Zoller produced a very nice set of ideas of how and the ion trap as it existed in the year 1994 would actually work as a quantum computer. And in fact, they revealed these ideas exactly at this meeting in Torino, in Italy. And that definitely resonated with my thinking as, well, the magnetic resonance didn't resonate, so to speak, but their ideas for the ion trap definitely did. And it got me thinking almost immediately that, well, there must be something general to this. And I began some studies, first of all, of saying, well, surely we have to take a very broad view of what could quantum compute. And this is in fact my own first paper in quantum computing, and it had a table of possible entities that might quantum compute. And some of them, I would admit, are kind of weird and definitely not, not in play nowadays. The Mössbauer nucleus, definitely not. But other things like electrons in gallium arsenide, yes, became a pretty important thing, but also nuclear spins, also trapped ions, although indium turned out not to be the preferred trapped ions. I had my own sort of Gedanken apparatuses for what a quantum computer might be based on scanning force microscopy, which is better left sort of unsaid. But what I realized in doing this was that, well, yes, there is something really systematic behind this, or something actually fairly universal. And it was that within those years, and then in its final form, as I wrote them in the year 2000, were these criteria. Now, I'm not going to spend a lot of time talking about these. I wrote them up very carefully as a chapter in a book. And that's the version that you should all read if you wish to. However, this is cut directly from Wikipedia, and whoever made the Wikipedia page did a great job. In particular, they used exactly my phrases for these, which I felt was important, rather than paraphrases. But more importantly, have a whole paragraph of descriptive text behind each of these criteria, because these should be read carefully. I mean, the careful choices of words were made, and then I gave explanations for why. And then also sneakily said, well, look, the NMR quantum computer surely can't do this, that they really had no good way of initializing the state of qubits to a simple fiducial state. So to me, that was actually a killer for that. But I also acknowledged that the Cirac and Zoller approach to ion traps checked all 5 boxes. So they definitely had effectively thought through each of these 5 criteria and had answers to all of them. And so when I did subsequent work, for example, on quantum dots, I really tried to make sure that these would be satisfiable. And they weren't always in the ways expected. For example, there's the statement that, well, the decoherence time should be long-lived. And when Daniel Loss and I said, we think that electrons in gallium arsenide, their spins would be very long-lived and would be a good qubit. We missed part of the physics of the nuclear spins, the other nuclear spins in the gallium arsenide lattice. And that's caused years of work. And finally, electrons in gallium arsenide are not actually the preferred qubit, quantum dot qubit, largely because of criterion 3. But luckily, there's an alternative, and there's very active research currently on electrons in silicon or silicon germanium structures. All right, so I'm actually rather near the end, and indeed, I wanted to leave a lot of time for discussion. I want to acknowledge that there are many ways of writing criteria for quantum computers. I've been asked if they should be updated, and I said yes, but not necessarily by me, because they should and have gotten much more specific. That is, well, what are the criteria for a superconducting processor to work? Well, you have to get way more specific about, well, you have to do quantum gates, and they have to be universal, and they have to be very precise. That was sort of understood. That is, in the year 2000, when I said decoherence times, I also meant other things, contributing to the imprecision of qubits. And boy, there's a huge amount of knowledge and lore and things that have to be checked that make it possible to really satisfy the detailed requirements for that processor. And then for a photonic quantum computer, the requirements are completely different. That the ability to measure the qubit, to measure the state of a photon, is key and difficult, and definitely a problematic part of making an all-photonic quantum computer. Let me move, though, to, I like to, do honor to another thinker who I think, while he was not, present at the early stages, well, in a sense was, because David Merman developed very original ideas about how you test for quantumness in the form of Bell inequalities, or the violation of Bell inequalities. But he wrote a beautiful book about quantum computers, which in its body is a nice, excellent undergraduate textbook for teaching quantum computers to a broad set of students. But his first page has some very beautiful, observations, and I won't read them all to you, but maybe I can just feature one or two of the words here that, because it's in a sense the last sentence that encapsulates the real difficulty of making a quantum computer. In a quantum computer, the physical systems that encode the individual bits, quantum bits, you might say, must have no physical interactions whatever that are not under the complete control of the program. Now, in retrospect, this is a little too harsh. That is, if it were really true, no physical interactions whatever, then we could forget about it. That there's no such thing in physics as no interactions. But controlling them so that they're at a very, very low level, yes, true. And that is the extreme difficulty of making a quantum computer. I'll close with some just sort of aphorisms in some sense. I'll indeed say that, of course, we've turned the corner, but this was already a long time ago, that we don't anymore have gatherings, where there are 20 people and they're the only ones who care about quantum computers, that we've been filling vast auditoriums with quantum computing enthusiasts, but already almost for 20 years. But the sort of phase transition of that indeed occurred in this period from the late 90s to the early 2000s. But I mean, of course, nowadays you could fill a whole Congress hall with people interested in furthering the science and technology of quantum computers. Here are a few thoughts to leave you with. Bennett, who was the, in a sense, forefather of quantum communication in the form of quantum cryptography, also quantum communication, has really a theorem that says that computation does not actually require consumption of power. That's a beautiful insight, however, not confirmed or not borne out by our current use of power. I think this statistic of 2% electricity consumption is a bit out of date, actually, that our use of power, I mean, really electric power in running computers is quite huge, despite Bennett's theorem. And another thinker of that time, of some time back, Margolis, observed and had mathematical models that said quantum computers could operate autonomously, but actually they don't. And the ones that we know how to build are heavily under the control of external agents. And to me, it's understood that a working quantum computer has perhaps more than a passing resemblance to a detector at a particle lab. This is not by no means the biggest one that exists in the world. This is one that's, I guess, been decommissioned at Fermilab, but it also has a vast amount of basically classical electrical technology surrounding a quantum core. And that's kind of looking like what a quantum computer will continue to look like into the future. So anyway, thanks for your attention. And we've reached the time when we can have some discussion.
Thank you so much, David, for this magnificent presentation. I really love the comparison with the Fermilab detector at the end. There are already many questions, and everyone get ready to ask all your questions. This started when you showed the IBM design. There were questions, can we scale this up to 3D? Are there any considerations there?
3D, well, at one level, 3D is already happening, and it's in the sense that chip engineers mean it, that they use 3D structures, meaning they use multi-layer structures. And it is known that some of the, for example, the first stage measurement apparatuses are best put on another chip. So they're put on a facing chip, facing the chip with the qubits. So that's a first step into 3D. Actually putting the qubits 3D is an interesting idea, and those of you who are looking very, very carefully at IBM's roadmap or have looked at it before see a little cartoon that implies that they will stack up, but they'll imagine stacking up whole modules. So they'll make a whole rather big chip with 1,000 qubits, let's say, and then to have 1,000,000 qubits, they'll stack 1,000 of those. So they have to have some interconnects among them. My current expectation, it will not be truly 3D in the sense there won't be qubit to qubit entangling operations between these modules. That'll all go via the edges, and the quantum computer will still be in a certain logical sense, still basically two-dimensional. So, but it remains an open story. Actually, for neutral atom structures, there are maybe more realistic ideas of how you would really go to 3D and have actual 3D connectivity, which is understood to be good for error correction, potentially. Maybe I'll leave it at that, though.
And Miguel Gonzalez from Mexico asks, when you were at IBM, and you were a theorist, but were there already plans back then to really build a quantum computer at IBM?
Yes, definitely. Well, it came in stages. IBM's work was purely theoretical until around the year 2000. And then the subject became sufficiently interesting, but it had to become sufficiently interesting to some IBM executives that they said, okay, now we would be welcoming if some of the experimentalists on staff would start thinking about this. And at that point, one experimentalist, really only one, who had experience in superconducting devices said, I'm going to try it. And he was encouraged to try it. And we teamed up. We were working together right from the beginning of that. I was starting to do modeling of superconducting devices, really motivated by his work. His name was Roger Koch. He tragically died suddenly in 2007, before IBM's program really got off the ground, but thereafter it really took off and became a very big experimental activity at IBM.
some people point out that the conference at Torino is really resembles the Solvay conference at 1927, if I remember well. That is wonderful.
Okay, well, it's sort of approximately the same scale. It also involved, it occurred because of a private benefactor, as did the Solvay conferences. It had a lot of people interested in very basic quantum mechanics. I'm sure we can come up with many, many other differences, though.
Yeah, I'm sure too. Mohammed Reza from Iran asks, will there have to be updates on your criteria if more advanced algorithms, even more advanced than Shor's or Grover's, were to be discovered in the future?
I would say no. I think that, well, I'm not updating algorithms anymore. Sorry, I'm not updating criteria. I think that these criteria would have been definitely not so useful if the promise of adiabatic quantum computing had really flowered. Now, that's still a going concern, but it's a very, very different approach to quantum computing, which Aharonov proved was, in some sense, some formal sense, also universal for executing quantum computing. The trouble is it has very poor tolerance to fault. So that's why I don't believe that adiabatic quantum computers will ever be really scalable, full functioning quantum computers. Those would really take a different set of criteria because they're not based on the idea of running quantum gates. But merely the discovery of new gate-based algorithms, no, I think, my criteria are just ones about how you build the machine, and the machine is supposed to be a universal machine, supposed to run any algorithm that's proposed within the setting of gate-based quantum algorithms.
Someone indeed also asked, how would we apply it to the D-wave quantum annealer? And
okay, I think I've said pretty much all I would say about that. There's certainly some quantum power to the D-wave computer, but it's also a very noisy quantum computer. And I think the jury is out on how far we can go before we can really suppress noise. I mean, this is an active and controversial subject that it seems there's a bit of an arms race now that a new generation of quantum computers is fielded, and then algorithms are run on it, and then there's a statement, oh, now we're finally at a stage where this is not something that could have been computed on a regular computer. This happened 4 years ago or 3 years ago in the so-called Google's quantum supremacy. It also happened 2 weeks ago in the IBM so-called quantum utility paper. And in both cases, groups from basically many-body physics came up and said, look, we have algorithms at our disposal that we can run on regular computers, and we can do these quite easily. So, despite the fact that it was expected that it would take 10,000 years of running time to reproduce, but in fact, it only took a few days of running time. So I think that arms race will keep going for a while, and may only be settled in the era of error correction, or it may be that just a regular, I'll say NISQ, I haven't used that phrase, noisy intermediate scale quantum algorithm, when run on a 1,000-qubit machine, will finally settle the issue, and there will not be an effective classical simulation of that, but we don't know.
Now a question to answer personally from Rupayan from India. What is your favorite qubit type and why?
Well, I've gone back and forth on that. I mean, I love spins in semiconductors, but that's partly because of my research orientation. I'm a solid-state physicist, and I love crystal physics, and I love the intricacy of semiconductor physics and how it can be applied. Now, having said that, though, the spin qubits, quantum dot spin qubits, have not taken flight. It's really one big technical problem, which is making entangling gates that work between qubits that are at a sort of intermediate distance from each other. What I mean by that is, for example, a micrometer, because we have excellent entangling gates at the nanometer scale, but that's too close. And the there's an architectural problem of how to spread the qubits out so that you can get all the control lines to them. There are great ideas for how that might be overcome, and over time, these qubits have continued to get better in the last 20 years. So the basic qubit is really good at this point, but that step is missing. Now, also, some days I say I love superconducting qubits because I've also been modeling them for years and years and years. So those are my favorites.
That is wonderful. And Maya from Iran also asked something related, which you, in my opinion, answered, because she said silicon-based quantum dots achieved a fidelity of 99%. What is the reason for superconducting platforms instead of quantum dot-based ones?
Well, there are two parts to that. One is that there is also a kind of arms race in fidelities. And I would say this is not a new message, but we understand that 99% fidelity is not the end point, is not actually good enough. Now, luckily, 100% is not necessary. That is, David Merman's comment was not true. That is, we don't need absolutely 100% perfect fidelity. But the experimentalists have recognized this, and they've been striving for, approaches that definitely go beyond 99%. And there are new results. Let's see if I can remember, if I can quote the number properly. 99.98, I think, is a number that one can quote, or 92. No, 99.92, I think, is a entangling fidelity that one can quote. And that's definitely way better than 99.0. I think that will become the standard. Now, how many nines do you need is a big question. And theory has said all along that about 3 nines is enough. But that's within the setting of fairly simple models. So we will see if it's enough. That is, it then gets tied up in all the sort of architectural questions of, can you really use to the full the fidelity that you've got, and you don't fumble it by doing some other thing wrong. And you should be able to do it all the time throughout an entire array of qubits. So we will see. And it gets to difficult experimental questions. I'll throw in one that these otherwise very beautiful superconducting qubits turn out to be susceptible sometimes to ionizing radiation. And so that causes the effect that most of the time they're 99.9%, but then an energetic particle hits them, which may happen only once a few minutes, and then it blasts it for, fidelity becomes very poor for a fraction of a second, and then it recovers again. And this has been very carefully investigated because some, kind of irreducible source of these are cosmic rays, are muons from cosmic rays. So people have done experiments deep under mountains to confirm that, yes, indeed, these are the source of some of the problems with coherence. But how do you precisely characterize something that's 99.9% almost all the time, except for, a few milliseconds out of a minute? This is sort of a new problem, but definitely a problem. So, but it's also a problem of how experimentalists communicate these results, because it's not captured just by the idea of fidelity. So you need good fidelity and better and more. And maybe we don't understand all the mores at the moment.
Let's look back a bit and also in the future. Ron from Chicago asks, some quantum professionals indicate that the current state of quantum hardware is akin to the vacuum tube state of classical computers. What are your thoughts? And Artem from Mexico asks, what is your vision for the distant future of the quantum industry?
Oh boy, okay. The first one's easier. Yes, I do kind of agree with that. I remember being quite struck in reading the biography of Turing, but you should look not at the famous part of Turing's career when he was cracking codes, but the years immediately after, when he actually became a private or a researcher at a university, Manchester, was it? But the point was that he joined a group that received among the first digital computers, but which was definitely a vacuum tube model. And he did definitely useful work with that. He made models of, how leopards get their spots and other sort of biological pattern problems by, running simulations. But his hardware was very shaky, and there are stories about him having to go into the basement and sort of kicking the machine, like to the magnetic drum, which hold, the memory drum would be a little bit defective, and he'd have to, kick it to make sure it was spinning properly. So, we're a bit in that stage where the basic hardware is just barely working well enough and definitely needs a lot of kicks. I'm told stories by people who use the cloud machine that, it's recalibrated regularly, I think more often than once a day, but that you really want to have the luck of having your run occur right after a calibration and not after a few hours, because then your results are definitely worse. That the machine is drifting and getting successively worse in a noticeable way. So maybe that's that. Now the other cosmic question was the far future. I don't know. I mean, I think any of you can have just as good an idea about that as myself. I was intrigued by hearing that people are thinking of putting data centers on the moon. So I think that putting a quantum computer on the moon would be a great long-term project. I then learned that people say that this data center, that we could do it, or we will do it very soon, because the first data center on the moon will be just a sort of like a terabyte disk that you just drop on the surface and make sure that it can communicate with Earth, and then, aha, there's a data center, a rather modest data center.
I think we should keep collaborating on that all together with all the input from different backgrounds from the group. There are still really many questions. We will pick a couple more, and for everyone there will be upcoming hardware lectures on the different qubit modalities and also on their architectures. So then we can continue the discussion on those. Caroline from Cameroon asks, do you think that we will discover a new material in the future that will change everything, as silicon did for the implementation of classical computers?
Always possible. I mean, maybe I should say yes, because the field of materials is so gigantic and the number of possible combinations is so large that I'm sure there will be such things. But planning breakthroughs in materials is notoriously, well, impossible. That and it seems the right prescription for materials is you just make sure there are experts around who are constantly mixing up new stuff, and you just keep watching what they make, and maybe encourage them to throw in things that are magnetic or things that are have a lot of hydrogen or something like that, some very broad guidelines, and just see what they manage to make. Definitely, like the current development of room temperature superconductors is a fundamentally materials thing, which has to do with the insight that you can make crystals that are almost all hydrogen with a little bit of other stuff. And that's an interesting combination for making really a new class of materials, totally unrelated to quantum computers. But, well, you have to allow a lot of freedom in that kind of research.
And like that, indeed, new materials define human eras. Let's see what is next. Yash from India really wants to know more about the qubit architectures. Why is Google's Sycamore or IBM's Osprey modeled the way they are? What is the physics behind qubit connectivities? Could you comment a bit on that, and it will discuss more in
well, that's a whole course worth of information. Just to touch on one or two thoughts. IBM and Google made quite different decisions about what their chips how their chips would function. Sycamore versus Osprey is a good example. Sycamore has what are called tunable couplers, which means that there's even extra control signals that don't go to the qubit, but go to the couplers between the qubits, and in a fairly explicit way turns it on and off. IBM chose not to do that, and they get all their turning on and off of entanglement by what signals are sent to the qubits themselves. in both cases, the couplers are electrical structures. They're typically, they exploit the physics, the electromagnetics of guided waves, and use the quantum mechanical properties of guided waves in resonator structures to couple qubits. That's enough of that lecture.
Perfect. And indeed, everyone, keep your questions ready for the virtual lab tours and hardware lectures there. Oh, Priyal from India also really wants to know more which technologies you really think have the potential to gear up the future of quantum computing. You already mentioned a couple of things.
Well, I think the only one that I showed you a big list, and I said many of them are in play. Maybe the one that fell out of contention and then came back are neutral atoms. I think that's an interesting coming subject that maybe 5 years ago would have said, oh, kind of interesting idea, but it's not working. And then now it's working. And by the usual standards, the high fidelity and many qubits and a lot of good control. And so we see several organizations now launching, order 100 qubit devices, either simulators, but also universal computers, quantum computers. So that's an interesting kind of new arrival, but not really so new. That is, we knew 25 years ago that there's good physics there that could be exploited. For the rest, it's just, keep watching the silicon, the germanium, the calcium ions, the ytterbium ions, the transmons, the other varieties of superconducting devices. I think the quantum computers will come from somewhere on that short list.
We will see it all the next coming years and decades. Taha Ruaba from Algeria, a quantum expert at Constantine Quantum Technologies, asks, what is your opinion about the recent developments at Google, Continuum, Microsoft in topological quantum computing?
Okay. One should make a distinction. There are topological ideas for quantum computing that are purely software, you might say, that are very tied up in how we define error correction codes. And some of the work that you hear about is indeed the realization of error correction codes based on topological principles. I mentioned Aharonov and Kitaev. Actually, it was mainly Kitaev's work that first, set that in motion. Now, when you talk about Microsoft, though, they put a bet on a rather different approach, which is to build or use topology to build the qubit itself, as part of the really fundamental constitution of the qubit, and that's in the form of we would say abelian or non-abelian anyons, or you might say the catchphrase is Majorana zero modes. This has had a rocky history in the last 10 years. There are beautiful ideas for how that would work. Requires quite exotic materials combinations, which Microsoft has worked hard on, and other researchers. But the sad state of affairs is that after 10 years of research, there's no qubit. So it fails to come to criterion 1. And until that's achieved, it's hard to say much more about what could be done. I mean, there are advocates, and definitely advocates within Microsoft, that say, when we have this as a qubit, it will have fantastic fidelity right off the bat. And so we'll leap over all these other approaches immediately. I say maybe, but until we have the qubit, there's no way of saying. And there are also plenty of studies that say, well, if you really look carefully at the, what might come, it might still have sources of noise that we have not really understood. So I'm not so optimistic about that approach.
We will finish with 2 questions with very quick answers. What is the quantum application that you are most excited about to see in future? That you expect there will
factoring.
be.
Factoring. Pure mathematics.
And then a futuristic question. Do you think quantum computers will be the end of progression in computing? Will there be anything above that?
Yes and no. I don't think there will be any further physical basis for computing, but I'm certain that the nature of computing will nevertheless continue to evolve in fundamental ways.
David, thank you very much for this fantastic talk. It was really an honor and pleasure to have you. Thank you for this great session.
Okay, dank u wel, Marlou.
Even in Dutch. Bedankt, David. Geweldig en een hele fijne avond. It was a great pleasure.
Voor jou ook. Okay. Yeah, thank you all for listening.
Oh, thank you very much. This was also by far the most questions. I know many questions have not been asked, but for some of them we can relay them to the next days where we can dive in depth for the hardware panel, the hardware discussions. Really looking forward to that with all of you. And David just mentioned one of the qubit modalities that really ramped up the past 5 years. And that is the topic we will discuss now with Jeff Thompson from Princeton, namely neutral atom quantum computing. So thank you, David, for also paving that way. And I would like to thank you once more for this great lecture and wonderful Q&A session before moving now to Jeff, whom I already saw being wonderful. Good to see you again, Jeff.
Hello.
David, thank you very much. Feel free to stay or to leave. Jeff, great to have you here. For some of you, Jeff might be a familiar face. He was here last year to present the virtual lab tour on neutral atom quantum computing. Jeff Thompson is a professor at Princeton University, expert in neutral atom quantum computing. He has done a PhD at Harvard, a bachelor at Yale University, and won a range of honors and awards, including the DOE Early Career Award, Sloan Fellow in Physics, Young Investigator Prize, Hearst Foundation Graduate Fellowship. We are really happy to have you here and now pave the way for everyone to dive into neutral atom quantum computing. I would like to point out that tomorrow also we will have Quera over to give a software bootcamp in neutral atom quantum computing, and getting ready for the other topics after that, namely trapped ion quantum computing, superconducting, photonics. We just had David DiVincenzo with us, who of course also explained the DiVincenzo criteria. So we hope that everyone will be able to identify those in your talk now as well, and get insight in the promises of this platform.
Yeah, great. Is that my cue?
Yes.
Okay. Yeah, well, it's a real pleasure. To be here. And what I'd like to tell you about today is a little bit of an overview to the field of neutral atom quantum computing, but then the majority of my talk will actually be specifically about the kind of work we do in my lab, which is developing a particular type of neutral atom quantum computer, which is one based on ytterbium atoms. So at a high level, this is kind of basically a picture I like of what a neutral atom computer looks like that encodes the essential elements of it. Not exactly explained along the DiVincenzo criteria, but roughly. So in a neutral atom quantum computer, the heart of it is a vacuum chamber where there's an array of atoms trapped inside, and these atoms form the qubits. So each atom is one qubit, and the qubit might be encoded or is typically encoded in the spin of the atom. And these atoms are held in tightly focused laser beams called optical tweezers. And you can make very large arrays of these laser beams up to tens of thousands using various kinds of optoelectronic technologies that already exist, like spatial light modulators and acousto-optic deflectors, things like that. To learn about the states of these atoms, to measure the qubits, we image fluorescence from the atoms onto a camera that you can use to actually see fluorescence from single atoms. And I'll show you many pictures like that later in the talk. And then to control the qubits, to manipulate them, we also use laser beams that are focused down onto the individual atoms to do both single qubit gates and 2 qubit gates. And finally, neutral atoms don't actually interact strongly with each other. There's no charge. But to make them interact in order to generate entanglement, to do 2 qubit gates, we excite them to very highly excited atomic states called Rydberg states. So those are the basic elements. And in the next few slides, I'll walk you through some of these components in a little more detail. So the first key technology that goes into making a neutral atom quantum computer is what are called optical tweezers, which is the way that we make an array of atomic qubits, neutral atom qubits, and hold them in place. This is now about a 20-year-old technology within atomic physics, and it's actually a very simple kind of laser cooling experiment. So this is a picture from our lab of a vacuum chamber, and that green cloud you can see inside is what's called a magneto-optical trap. It's a laser-cooled cloud. There's about 1 million ytterbium atoms in there, and that green light you're seeing is the fluorescence from the atoms. That's at 556 nanometers. So then, to make these optical tweezers, what we do is we put a microscope objective on top of this vacuum chamber, and then we take a laser beam that's detuned away from the resonance from the atoms, and we focus it down through this objective, and that makes this very tight tweezer potential for the atoms. And then we can image fluorescence from the atoms onto a camera so we can see what comes from just that tiny volume where the optical tweezer is. And so going back more than 20 years to this, pioneering the first demonstration of optical tweezers from the group of Philippe Rangier in Paris, what happens when you do this experiment is that you see that the amount of fluorescence on your camera goes back and forth between a low level and a high level. And if you look at sort of what these pictures look like, you see that it's just a single bright spot. So what you're actually watching here is single atoms from this magneto-optical trap coming into this optical tweezer and then leaving again. It actually turns out the reason they leave most of the time is because a second one comes in and then they kick each other out through a process known as light-assisted collisions. And this is a really fortunate thing that happens in these traps because it means you can deterministically prepare one atom in the tweezer by just, for example, stopping the loading once you already get one atom. You don't have to worry about the possibility that you have 2 or 3. Now, in this example here, the time that the atoms stay in the optical tweezers is not that long. It's only a few seconds because, and it's limited by the rate at which additional atoms come in. But if you stop this loading process by, for example, getting rid of the magneto-optical trap around the atoms, then you can keep these qubits for basically as long as you want, just limited by the quality of the vacuum in your vacuum chamber. And the current world record is, I think, around 2 hours. So that is how you make these optical tweezers and get atoms in them. But this kind of stochastic loading process where atoms come and go creates a more fundamental problem if you now want to make a large array of, say, hundreds or thousands of qubits, because if you just stop the loading at some particular time, the probability that any given trap is loaded is about 1/2. So the probability that 1,000 traps are simultaneously loaded is 1/2 to the n. That's quite small. But there's an important idea that was demonstrated for the first time now, about 7 or 8 years ago, which is called rearrangement, which is based on the fact that not only do these atoms stay for a long time once you turn off the loading, but you can also take a picture of which sites are filled, and even that arrangement of the atoms will survive the picture. So the idea of rearrangement then is you start out, you initially load your tweezers, and there's some random subset of the sites are loaded, but then you take a picture, and the atoms stay where they are, and then you compute in that given shot how you can move the atoms to create an array without defects. So in a one-dimensional system, what you can just do is squeeze out all the empty sites, just compress all the empty sites to move all the atoms to one side. But in 2D, there's also more sophisticated algorithms you can use to pick up individual atoms and move them into the right place. And people have also even done this in 3 dimensions. So this idea of rearrangement now allows you to prepare deterministically arrays of, I think the record is currently maybe 300 or 400 qubits. Okay, so the second key technology that goes into a neutral atom computer is the question of how to make these atoms interact with each other so that you can generate entanglement. If I just have 2 neutral atoms sitting in their ground state, they really do not know anything about each other at all. They don't feel each other's presence at all. And that's actually in some ways beneficial because it means there aren't interactions going on when you don't want there to be interactions. But the way we can turn on interactions to do gates is to excite atoms from the electronic ground state using a laser to a very highly excited state called a Rydberg state. These are states where the principal quantum number maybe goes from n = 5 to 50 or 100 or something like that. And what is interesting about these states is that when you go to these very high-lying states, the electron orbit around the atom gets very big. It actually grows as the square of that principal quantum number n. So if the ground state of, say, a rubidium atom, which has n = 5, looked like this, a Rydberg atom with n = 50 would be this much bigger, and n equals 100 would be even 4 times bigger again. And so these electron wave functions can get almost to be micron sized. And then correspondingly, these very large and fluffy electron clouds are very polarizable. This polarizability actually grows as the 6th or 7th power of the quantum number. So what that means is the van der Waals interaction between two of these, which is related to polarizability, grows even faster. This actually grows as the 11th power of the principal quantum number. So what the fact that you have this interaction that grows extremely rapidly with n means that even though you have very small interactions in low principal quantum number states, you can switch on extremely strong interactions to do very fast entanglement and then come back down to turn off the interactions when you're done. There's many different ways to use this interaction to generate entanglement, but the most common approach is something called the Rydberg blockade. And the idea of the Rydberg blockade is as follows. So if I have one atom by itself and it's just got a ground state and then some highly excited state called a Rydberg state, and I'm coupling between them with a laser, I could drive Rabi oscillation, say, on this transition all day long. But if I now put this atom near another one that's already in the Rydberg state, the van der Waals interaction between them shifts or basically increases the energy cost to excite the second atom into the Rydberg state. And if the amount by which it shifts this state, U, is larger than the laser Rabi frequency omega, then this excitation is blocked or blockaded. You can't do it. So this is how the state of one atom, whether it's in the ground or the Rydberg state, can control the excitation of the second one. And the thing that's nice about the Rydberg blockade as an interaction mechanism is that it doesn't actually depend on what the precise value of this U is, so long as it's very large compared to the laser Rabi frequency. Right. So the way we always summarize the Rydberg blockade is that there's a characteristic radius, the blockade radius, and you just cannot excite two atoms to the Rydberg state simultaneously within that radius. For typical atomic parameters and laser parameters, this blockade radius tends to be between 5, 10, maybe 15 microns, which it works quite well with optical tweezer technology, where we can typically make tweezers with spacings of 2 or 3 or 4 microns. So the fact that this blockade radius is a couple of sites, but not infinitely many sites, is a really ideal length scale. And then the last ingredient is that, on that last slide, I showed you sort of a 2-level atom that has a ground state and a Rydberg state. But if you really would like to encode a qubit for a long time, you'd like to actually use multiple ground states that are stable that might correspond to different configurations of the electron or the nuclear spin. And you can also use qubits like that and entangle them through the Rydberg state if you have the ability to selectively excite only one of the 2 qubit states to the Rydberg state, which you can get by just tuning your laser to a particular frequency. So you can only excite one of them. So it's a little more intricate to understand how you do actually gates in this case, but the basic gist of it is that if I have, say, a pair of qubits and only one of the state 1 goes to the Rydberg state, if only one of them is in the 1 state, then the dynamics of the excitation of the Rydberg state is not affected by the fact that there's 2 qubits. But if I have both of them in the 1 state, then the blockade kicks in, only one of them can go to the Rydberg state. That gives you some different excitation dynamics that you can turn into a 2-qubit gate in various ways. And so the current record fidelity for 2-qubit gates is actually, it was 98% for a while, and it's now, in the last couple of months, 99.5%. From Misha Lukin, Vladimir Vuletic, and Marcus Greiner's experiments at Harvard and MIT, which is now basically in the mix of what the state of the art is for any other qubit platform. So I don't want to read too much into what David DiVincenzo said in his last talk, but I think it's this kind of line of experiments here that have maybe showed that this is now a very compelling technology for quantum computing.
And there are a couple of questions.
Oh, sure.
To repeat a little bit, Varda asks, how do you keep the atoms in such a high excited state, and why does the blockade actually take place? Could you review again?
Well, so they don't stay in the excited state for very long. We basically put them up there with a laser, and then we bring them back down when we're done. And we don't want to leave them up there for too long because they have some probability to decay on their own, and that would be an error in the gate. So we basically like to get in and out of that state as fast as possible.
Can you share more? What's polar? Oh yeah, go on.
Well, what is the blockade? So I mean, okay, I think it's maybe something you learned from chemistry class, that the van der Waals interaction, which is sort of just generically responsible for why things stick to other things, comes from polarizability. That basically, if you have many objects tend to lower their energies in an electric field. And so when you put two polarizable objects near each other, they want to stick together and you get this 1/R6 interaction. That's basically the same thing that's going on with these Rydberg atoms. So by making the electrons so big, you make them very polarizable so that they respond very strongly to electric fields. And when you put them near each other, they respond very strongly to each other's electric fields.
Great, and with that, you also answered what polarizability is, and we are ready to continue.
Great. So there have been a couple of, so it's an exciting time for neutral atom quantum computing, and there have been breakthroughs in gate fidelities just in the last year, but also in other really important ingredients for quantum computing, like being able to do, mid-circuit measurement, measure some of the qubits in the middle of a circuit, which is important for error correction, and also the Lucan collaboration at Harvard and Mark Saffman's group at the University of Madison, or Wisconsin-Madison, have also demonstrated in the last year the first, what I would call like programmable quantum circuits, where they have many qubits and they can specify a sequence of gate operations and run them. So all of this just in the last year or two, makes it a really exciting time for neutral atom quantum computing. So I'm going to switch gears now and tell you about the work that we do in my group and where that comes into the field. So where we started, with our experiments about, 6 years ago at this point, was, so everything I showed you up to this point was done with the alkali atoms. These are atoms that are hydrogen-like. They have just one valence electron, and they have a very simple level structure. But a few years ago, we started looking at the next most complicated atoms on the periodic table, which are these alkaline earth atoms. These have two valence electrons. They're basically like helium. And some of the widely studied ones are strontium and terbium. Even though terbium is down here, it has the same electronic structure as its friends over here. And these atoms have some interesting properties that make them useful for lots of things. So the particular the difference in the level structure of these that you get from having two electrons is that you have now both singlet, those two electrons can have their spins anti-aligned, in which case the total electron spin is 0. Those are called singlet states, or they can have their spins aligned, and that makes a triplet state. And transitions between singlet and triplet states are forbidden, which means they happen much less frequently. So that gives you generically two different kinds of optical transitions, ones that are like allowed between, say, singlet states or between triplet states, and ones that are between singlets and triplets, which are narrow and forbidden. And this turns out to be really advantageous for laser cooling, because these broad transitions let you cool fast to get from room temperature down to low temperatures, but these narrow transitions let you cool to extremely low temperatures, because the fundamental limit of how cold you can get an atom, called the Doppler temperature, is actually related to the line width of the transition. The second thing that's really nice about these atoms is that in the ground state, when the two electrons are sort of anti-aligned to each other, so there's no electronic spin, if you have an isotope that has a nuclear spin, that nuclear spin doesn't couple to anything. It just is very isolated. So it actually makes essentially the best qubit you could imagine, because it has very little sensitivity to magnetic fields or to optical fields. The third thing that's interesting about these atoms is, well, this is the true ground state is a singlet state. There's also the lowest energy triplet state also has a very long lifetime, even though it's not technically stable. In a terbium, this state has a lifetime of a few tens of seconds. And it also still has no net electronic spin, so you can also put a qubit here. And this is actually what I'll talk about in this talk, is explaining why it is that you actually want to do this into what we call this metastable triplet state. And then the last thing that we won't get into too much, but is that it turns out that once you go to these Rydberg states and these alkaline earth atoms, you now have a trapped ion inside the Rydberg state, because when you take these two valence electrons and you put one of them in the Rydberg state, you're now left with one valence electron inside. This looks like an alkali atom. And you can use the optical transitions of that ion inside the Rydberg atom to do a lot of interesting. So I don't claim to have explained all of these things in detail, exactly why you should care about them, but the actual picture I want to leave you with is that this slightly more complicated level structure is a little bit like a Swiss Army knife. So, when we started working on this a few years ago, we knew that there were lots of interesting and weird features in here. We didn't actually know what they were all going to be good for, but kind of in a somewhat literal sense, our research program over the last 5 years has been just opening this Swiss Army knife, pulling out various tools and seeing if we can find something useful to do with them. Okay, so with that, there's two main things that I want to tell you about from our own research in this talk. The first is about a new kind of neutral atom qubit that we recently demonstrated, which is based on this metastable state in ytterbium. But before I can tell you about that, I want to explain why it is that we're interested in this kind of qubit. And it is based on a theoretical idea that we developed a few years ago in collaboration with Shruti Puri at Yale and Shimon Kolkwitz, which is a new idea for how to do quantum error correction efficiently using an approach called erasure conversion. So in my remaining time, I'll probably spend roughly equal time on these two things. So in a quantum computation, the fact that errors can occur is basically the main obstacle right now. If we had perfect qubits where you could do perfect gates, I am sure we would be factoring large numbers and things like that already. But the fact that the qubits have decoherence, gates have errors, is the problem now, in no matter how you look at it. Fortunately, there's still a path to doing quantum computing, and what that's based on is quantum error correction. And quantum error correction is essentially the idea that you can take the information that you're trying to compute on and encode it redundantly into not just one qubit, but several qubits, so that if an error happens to one of them, you can use the remaining information in the others to recover the state that you care about. Error correction is also a well-developed idea in classical computing and communication. And to give you just the simplest example of a classical, by which I mean not quantum, error correcting code, let's consider that I have a channel where I can just send bits of information to somebody that I want to talk to, but it's noisy, so they don't hear some of the bits the right way. So if I want to actually send the information 0, then what I could do, instead of just sending 1 0, I could send 3 zeros, so redundantly encoding it. And if I want to send 1, I could send 3 1s. And then the receiver, the person who's listening on the other side, will use a very simple algorithm called majority vote to decide what message I intended to send. So if I sent 0 0 0, for example, and the middle bit got flipped to a 1, they will still understand that I meant to send 0 because they say, well, there were 2 zeros and 1 1. So it's most likely that they sent 0. However, it is also possible that I tried to send 1 1 1 and then had 2 errors. And if they get this message, they will still conclude that I intended to send 0, even though I actually meant to send 1. So this is a mistake. So this error correction isn't perfect, but it can recover from any single error that occurs in the channel. So there is a quantum version of this too, which at a glance is sort of an obvious generalization that if I want to send a quantum state, alpha 0 plus beta 1, there's a superposition of 0 and 1, then I would again use this redundant encoding to send alpha 0 0 0 plus beta 1 1 1. But there's a problem now, which is that if the receiver wants to do the majority vote kind of operation that we described previously, it seems like they would have to look at the qubits to ask, well, are they the same or not? And if they just go and measure the qubits directly to figure out, whether there's more zeros than ones, they're actually going to collapse this superposition and destroy the quantum state that we were trying to transmit in the first place. But a really important idea from Peter Shor is to instead to still look at the system, but to be very careful about how you measure the qubits. And instead of just measuring the qubits, you just ask exactly the question you want to know the answer to, which in this case is about the relative parity of 2 qubits. So for this code here, I can learn about whether any of the individual bits have errors by asking 2 special questions. The first is, are qubits 1 and 2 the same as each other? And the second is, are qubits 2 and 3 the same as each other? And I can do those checks using some extra helper qubits called ancillas and gates like this. And in basically this circuit here, I'm going to flip this ancilla, depending on the state of these 2 qubits, and flip this one depending on the state of these 2. And in the end, by measuring these 2 ancilla qubits here, I learn from the measurement of this one if the first 2 qubits are the same. And from this one, I learn if the second 2 qubits are the same. But importantly, I never learn whether any of these qubits are 1 or 0. So this allows me to tell where errors have occurred without actually destroying the superposition. This particular code can actually only correct bit flips where a 0 becomes a 1 and a 1 becomes a 0, but not the other kind of quantum error that can occur that's a phase flip, where like say 0 plus 1 becomes 0 minus 1. But there are generalizations of this that can also handle that. So a really important idea in error correction is the notion of a threshold, which is related to how many errors you can correct. So I argued earlier that for this kind of repetition code, classically where I encode 1 bit in 3, I can correct 1 error, but it fails if I have 2 or 3 errors. So I can actually overcome that by using more copies instead, right? So instead of using 3 copies, I can use 5 or 9 or 4,000. And then it turns out if I use D copies, I can correct basically D over 2 errors, which is intuitively makes sense given that it's majority vote. However, this isn't totally for free because when I use more copies to encode my message, I also create more places for errors to occur in the first place. So even though I can use an arbitrarily large code to correct an arbitrarily large number of errors, that doesn't mean I can always transmit information. It turns out there's and the way we think about that is that there's actually a threshold error rate. So if the error rate of the channel is below some threshold, then I can use essentially arbitrarily large redundant encoding to get whatever high fidelity transmission I want. But if the error rate of the channel is above that threshold, then by using redundancy, I'm just creating more places for errors to occur, and more errors are occurring, so I don't win at all. And so the way we usually think about thresholds is we plot what's called the logical error probability, or the probability that the receiver gets the correct state as a function of the probability that each bit has an error. And I've shown this here for different distance codes, different amounts of redundancy. And so here the threshold is at 1/2. It's where all these lines cross. And what you see is below the threshold, increasing the distance makes things better. Above the threshold, increasing the distance makes things worse. So error correction only works if you're below some threshold. Right. And then the other important point is that even when you are below the threshold, so you need to be below the threshold. Once you are below the threshold, the only thing that matters actually is the ratio of your error rate to the threshold. So your errors are sort of exponentially suppressed with distance if you're below the threshold, and what matters is how far below the threshold you are. Okay, so this threshold property can be extended to quantum circuits too. It's a little bit harder to analyze in that case because in quantum circuits, the relevant errors are actually almost always occurring during the gates themselves, not just in qubits that are stored. And the reason that's more complicated is now when you use, if you want to analyze the performance of a code, you have to consider, not only correcting errors that occur on qubits coming in, but also errors that are induced during this checking process with these ancilla qubits. And now this actually increases the cost of redundancy because now if I use a larger code with more qubits, not only do I have more qubits that have more errors, but I also have more gates where errors can occur. So unfortunately, it actually turns out for quantum computing that the best threshold that we know of for sort of a generic error model is from this code called the surface code. And that threshold is about 1%. And so this 1%, it's a lot lower than the 50% I showed you on the previous slide. But on the other hand, it's about where a lot of qubit platforms are right now. But still, you'd like to be very far below the threshold. So one area of research now in quantum computing and quantum error correction is to try to figure out how to raise these thresholds. And it could be, we don't know that it won't be the case, that somebody will come up with a better error correcting code that just allows you to have a much higher threshold under sort of generic noise assumptions. But the fact that nobody has improved on the surface code in, I don't know, probably 15 years or so at this point suggests that maybe that's not the case. However, there is another approach, which is to cheat. And the way you would cheat is by basically trying to design qubits that don't have all possible kinds of errors with equal probability, but where you can suppress some of the errors a lot, maybe intrinsically in the design of the qubit. And if you have a restricted kind of error model that can occur, then that can allow you to raise the threshold. So one example that's been widely studied in the last sort of 4 or 5 years and has inspired the design of a lot of new qubits is something called bias noise, where say now bit flips occur more often than face flips, for example, or vice versa. And so this is stimulated. And so in this case, it's kind of known that you can get thresholds for the surface code and its friends maybe into the as high as 5 or 6%. And this is motivated sort of specifically by what are called Kerr-Cat qubits, which is a type of superconducting qubit. And also it's motivated people to think about different ways to encode qubits into neutral atoms and ions and things like that. But it actually turns out to be a little bit hard to get this bias noise to work at a circuit level, because you need sort of special gates that don't convert bit flips into phase flips, and that is not always possible. So there's another, so where we kind of got started with our work was to kind of think about a different kind of special noise model that you could have in qubits. And that noise model is to have qubits where most of the errors are what are called erasure errors. So the errors that I showed you before were in a quantum context, we call depolarizing errors. You have bit flips or phase flips. But what an erasure error is an error where when it occurs on some qubit, you know that qubit has had an error. Like the qubit has an error and then it lights up or something like that. And you have that information about which qubits went bad. And even classically, we can understand why these errors are easier to correct. Okay, if I'm doing majority vote on this repetition code here, it's clear that if more than half of the qubits have had errors, then my majority vote is going to get to the wrong answer. But if instead I know which qubits have had errors, I can exclude them from the vote. And you can see in this example that even if I have 2 of my bits that have had errors, I can still get to the right state because I just look at the one that didn't have an error. And actually, even if all 3 of them had an error, I can still tell that there's an error. So I'm like never wrong, but I can correct a much larger number of errors. And it turns out if I generalize this to a distance D code, instead of being able to correct D over 2 errors roughly, I can correct D-1 errors. So for this, the advantage here really grows as you go to larger numbers of qubits. And this actually fact that you can correct twice as many errors is a property not just of twice as many erasure errors as depolarizing errors is a property not just of this example, but of any quantum or classical code. It's almost true by definition. And so this helps a lot in terms of the thresholds. Classically, the threshold actually, if you just have these erasure errors, is basically 1 because you don't pay any cost. If you use a larger and larger redundancy, you just increase the odds that one of your bits gets transmitted without having an error. So together with my collaborators Shruti and Shimon, we kind of thought that this was a neat error model, and what would it look like to have a qubit that had these kinds of errors? So then we started looking at our neutral atom qubits, where we have the qubits stored in the 2 spin sublevels of the ground state. And in these kind of neutral atom qubits, by far the dominant error that we have to deal with comes from going to these Rydberg states during the 2-qubit gate. Because when we go to the Rydberg state during a 2-qubit gate, we have to stay up there for enough time for the gate to happen. But this state doesn't have an infinite lifetime. It has some probability of decaying while we're up there. And so those decays are actually the dominant gate errors, the ones that you fundamentally can't get around. If you just had these 2 ground states and this Rydberg state, when you decayed, you would come back down to one of the 2 qubit levels, and that would be a depolarizing error. But what we realized is that if we use instead this metastable state in a terbium, then these decays actually overwhelmingly go either to the real ground state, where we can detect them immediately by just trying to get the atom to scatter fluorescence, to scatter photons, emit light on some transition out of the ground state, or they get trapped in other Rydberg states where we can also see them at the end of the gate by basically blowing up any of the atoms left in Rydberg states, converting them into ions, and then detecting fluorescence from those ions or doing something else. And it turns out if you go through the branching ratios here, that only 2% of the time that you decay from this state during a gate do you actually come back to the qubit subspace and stay there, which means that 98% of the errors that occur in these gates are detected and thereby converted into these erasure errors that are much more favorable. So with that idea, that erasure errors would be better, and here's a specific implementation for how to do this with atomic qubits, we then asked ourselves, well, how much would this actually help? How would this work? So my collaborator Shruti and her students simulated how this slight variant of this surface code called the XEZX surface code would work with this error model where 98% of the erasures, 98% of the errors are erasures. And the way in which they kind of envisioned this in the simulation is that we have this is a parity check circuit that's used in the surface code. It's a little bit more complicated than the one I showed you earlier. But after every 2-qubit gate, which is where the errors can occur, you check to see if any of these atoms have decayed outside of the qubit subspace. And if they have, you see that fluorescence that converts it into an erasure error. And then, because you blew up that qubit, you replace it with a new one. So in this model, what they found is that the threshold increases from the typical surface code value of around 0.9% to 4.1% if we let 98% of these errors be erasure errors. So this is a very significant increase, a 4-fold increase in the threshold. And what you can see is that this gives you, first of all, makes it much easier to get below the threshold, but also dramatically reduces your logical error rate in some cases by 5 or 6 orders of magnitude, even when you're far below the threshold. So this can make error correction a lot easier and can make it a lot more effective. So that's essentially the idea. And then once we had this idea and worked it out, we then set about trying to do this in the lab. And so that's the next thing I'll talk about, but I can pause now for a second if there's any questions that have come up about kind of the fundamentals of error correction.
Yes, great, Jeff. Varda from India asks, how do you come to know a qubit has an error when measuring can disrupt the quantum states?
Well, so in the kind of the generic model of a quantum error correcting code, you have to be basically very careful. The answer is you have to be very careful about how you measure. Because I can't measure any of these qubits directly. I have to use these ancilla qubits to just ask restricted questions, right? So asking whether qubits 1 and 2 are the same doesn't actually collapse this superposition. So you have to be careful about what questions you ask. In this erasure context, though, it's a little bit different here. Now we have basically, because most of the errors that occur actually result in the qubit, the atom leaving the 2 special states that I call our qubit states and going to some ground state or turning into an ion or something like that, I can make these measurements without disturbing qubits that are left in the qubit space. And I guess technically the reason I can do that is that the wavelength of light I'm using to sort of interrogate whether the atom is in the ground state or has become an ion is very, very, very far detuned from the wavelength of light that would excite atoms out of these qubit states. So these qubit states are sort of invisible to that measurement process.
Then Victor from Mexico asks, so the idea is that if it glows, I can know that there is an error and just got adjusted.
Exactly. And this is not, and it's very, I think the analogy I often use is that it's like bad handwriting, right? If somebody writes you a message and their handwriting is really terrible, you're not actually very likely to read, a Q as an R or something like that. You're most likely to say, I just have no idea what this says. And so we're a little bit kind of trying to do the same thing with qubits.
Then Always had already asked a question earlier. Thanks again. Thanks for asking again, Always. He asks, how do you stabilize these neutral atoms? Do the Rydberg atoms, are they more prone to decoherence than other photonic counterparts? And how long can they remain entangled? Many questions.
I'll show you when we talk about the experiment in the next bit. We'll get some actual numbers, I guess, which will maybe put that into context.
Excellent. Then the last question about error correction. Juliana from Italy. Do you believe that these new error correction techniques will accelerate universal quantum computation on neutral atoms?
Yes, in fact, not only in neutral atoms, but I think also in other platforms. And I think the last slide in my talk is a little bit of a commentary on how this can be adopted elsewhere.
Okay, looking forward to that. Let's move on.
Great. Okay, so in the next part of my talk, then I'll tell you about how we went and actually implemented this metastable qubit in terbium atoms in our lab, which was again motivated by this, earlier theoretical idea we had that this would be a good idea. And so these are the students and postdocs in my lab that actually did this one. So here is a picture of the vacuum chamber that actually defines our experiment. It doesn't look like this now. It's surrounded by optics and lasers and is glowing all over the place. But this is what it looked like before we just, when we first put it together. So the very basic atomic physics of how this works is that we have an oven where there's just a chunk of a terbium metal, and then it goes through several stages of laser cooling to end up as a magneto-optical trap inside this glass vacuum chamber, this glass cell over here, which you see this picture of here. And then we put the microscope objective on top of it, which is basically how we create the tweezers and measure what the qubits are doing. In our kind of best experiments these days, we can make arrays of about 400 different optical tweezers, and then about half of them get filled. So there's probably 200 plus or minus 40 atoms in this picture here. Right. So I guess I'll give you sort of a high level overview of the kind of results we have for different gates in this platform, and then talk about them in more detail. So the 2 qubit levels are the up and down nuclear spin states in this metastable 3p0 state. And we can do single qubit gates just by driving the rotation of that nuclear spin. And these work extremely well. We have sort of typical single qubit gate fidelities of about 99.9%. And then we do 2 qubit gates by selectively exciting one of these nuclear spin levels to the Rydberg state. And there we can also do high fidelity gates, a little bit worse, but about 98% fidelity. One of the things that's really important for demonstrating this kind of conversion of errors into erasure errors is that we have the ability to detect population in this ground state without disturbing qubits that are in this metastable state. And so to do this, we actually have 2 different kinds of pictures that we take of our atomic array. The first, we use this sort of green intercombination transition. These are the ones I've showed you before. These are extremely high fidelity images, 99.5, 99.6% fidelity. But in order to get enough signal to get this really high fidelity and keep the atoms, these images are a little bit slow. They're a few tens of milliseconds. And what that means is that if we tried to use this to look for population that had leaked during a gate, we would have some probability that this state decays during that image, and it would basically induce errors. So to avoid that problem, we actually introduced a second kind of image where we use this fast transition. And here we can take a picture in just 20 microseconds to tell if an atom is in the ground state or not. So this is much faster now. The probability of this metastable state decaying during this image is very small. It's also pretty high fidelity, but the downside is that by taking this fast image, we heat the atom up so much that it escapes from the trap. It doesn't survive at all. So we can't use this for rearrangement, but it's very good for detecting these erasure errors. And we don't care that the atom is lost when it's already had an error, because it's already had an error. So there's no information in that qubit that we needed. So I guess this is maybe very technical for you guys, but the first thing we have to do is actually prepare the qubit into this metastable state. You can actually drive the transition from the ground state to the metastable state directly with a laser. In fact, doing that is the basis of the world's most precise atomic clocks, called optical atomic clocks or optical lattice clocks. But it's actually very technically demanding to do that because it's such a strongly forbidden transition. So what we developed instead is a technique to initialize the atoms into here based on an approach called optical pumping, where we excite the atoms to a higher excited state using only allowed transitions, and then just let it decay into the state we want. And to measure the qubits, we at the end of the circuit, we basically do the reverse process where we optically pump them back down into the ground state. And the combined fidelity of this initialization and readout process is about 98%, is limited by some effects that we understand in this depumping process. So somebody asked earlier about coherence time. So this is a very important number for all these qubits. So the lifetime of this metastable state is about 3 seconds in our optical tweezers. If these atoms were just floating in free space, it would be 20 seconds. The reason it's a little bit shorter is that in the very intense light of the optical tweezers, there's actually processes like Raman scattering and photoionization that can kick the atoms either out of the trap or back down to the ground state. We were actually expecting it to be entirely this Raman scattering process, which would be linear, which would have a rate that would be linear in the trap power. We were surprised experimentally to find that it's mainly dominated by a quadratic thing that is, we think photoionization. But for the typical trap depths that we operate at, it's still mainly Raman, and this lifetime is about 3 seconds. Okay, so that is in some sense how long we can store a state in that metastable qubit. However, it's not exactly the same thing as saying that the coherence time of that qubit is 3 seconds, because it turns out that in that 3 seconds, if we prepare a qubit in the 0 state, say the nuclear spin down, it basically never flips to 1, to the other state, to 1. So the probability of that kind of T1 error in this time is essentially 0. Or this T1 process, we could say, is suppressed by more than an order of magnitude compared to the metastable decay. And similarly, if I prepare a superposition, the decoherence rate is also very slow. So we've measured that T2 star, the kind of Ramsey coherence time, is about a second, but the more relevant number is T2, which is the sort of the Hahn-Echo coherence time, and that is also much longer than this metastable state lifetime. So while the coherence time of this qubit is 3 seconds, the important thing about that is that 3 seconds is actually all decays out of the metastable state and not errors within the metastable state. And what's really important about that is that these errors that are decays out of the metastable state, we can detect them and convert them into these erasure errors that are more favorable. So the first thing about that, so let me show you how we do that. So rather than just characterizing just the decays out of this state while we're waiting around doing nothing, what we instead characterize is the rate of decays out of the state while we're doing a whole sequence of single qubit gates rotating the nuclear spin around into different states within that metastable state, which we do again with a radio frequency magnetic field. So and the way we characterize the performance of a circuit like this is using a technique called randomized benchmarking, where I prepare the qubit in some particular state, say 1, and then I do a very long string, in our case up to several hundred single qubit rotations, and then at the end, I put in a final rotation that's chosen to bring the qubit back to a particular state, in this case, the 0 state. And I look at how the probability to find the qubit in the right state at the end decays as a function of the length of the circuit. And from that, from this exponential decay, I can extract the error probability per gate, or the fidelity. And so if we do this, just ignore, not worrying about capturing the decay from the metastable state, we see that we have this baseline fidelity of about 99.9%, or a 1 × 10⁻³ error rate. But if we now augment this randomized benchmarking circuit to periodically, in the middle of the circuit, check to see if there's any qubits that have decayed out of this state, converting those errors into erasure errors by doing these fast images, we can now analyze the data slightly differently and look at not only the total probability that we find the qubit in the right state, but also the probability that we find the qubit in the right state, given that we didn't see any errors occur in the middle of the circuit. And this conditional probability is quite a bit higher. It's now 99.96%, which means that we converted basically 60% of these errors into erasure errors. And we know from other experiments that about 20% of the time the qubit is lost and we didn't see it, and then about a quarter of the time there's an error within the qubit subspace. But so from this picture here, we essentially see that we did successfully do the thing we wanted to do, which is make this metastable qubit where we can see when errors occur and convert them into these erasure errors. And so this is the first experimental demonstration of this idea that we set forward a few years ago. And there's 2 key properties about this detection of errors as erasure errors that I want to emphasize. The first is that the information that we use to tell if something is an erasure error, we get from measurements that we do in the middle of the circuit while the qubit is still in an arbitrary superposition of 2 states. So along the lines of the question somebody asked earlier, these measurements that we're doing to check did the qubit leave the computational space or not, do not disturb the qubit if it has not had an error. And I guess the second point I want to make is exactly that, but a little more quantitatively. So we not only do they not introduce a lot of errors, but we know, in fact, that they introduce an error that's less than 1 × 10⁻⁵. It's about 5 × 10⁻⁶. And the reason these errors are so small is that the light that we use to do these measurements is very far detuned from the qubit state, and the image, the amount of time that it takes us to make one of these measurements is extremely fast compared to the qubit light. So this is, in some sense, this is a very good measurement in the sense of not disturbing the qubit. So that demonstration of the sort of single qubit erasure conversion lays out the basic principles, but for where this is really important is for the dominant errors, which actually occur during the 2 qubit gates. So the way we do 2 qubit gates is by, as I outlined earlier, exciting one of the qubit levels to the Rydberg state by basically ensuring that our laser is tuned to the right frequency to do that, so that it can't excite the 0 state. And the type of gate we use is there's many ways to do these Rydberg gates, but the type we use is a particular gate called the time optimal pulse, developed by our collaborators Sven Jandura and Guido Pupillo at Strasbourg. And it essentially results in some complicated evolution on a Bloch sphere that gives you a geometric phase that's different by pi, depending on whether you start in the state 0, 1 or 1, 1. And this effectively implements a CZ gate. And what the pulse actually looks like experimentally is we turn on our laser for about a microsecond at this frequency, but with some phase modulation across the pulse that's responsible for making sure that it works the right way. So to characterize how well our 2-qubit gate works, the first thing we do is prepare just entangled states of a bunch of isolated pairs of atoms, Bell states in particular, and then we can measure the fidelity of these Bell states by using a technique called parity oscillations from the trapped ion kind of community 20 years ago. Whoops. And what we learn from these parity oscillations, if we go and we measure without doing any corrections at all, we see that the Bell state fidelity we get is about 86% at the end of the circuit. But then if we correct for the preparation and measurement errors, which we've modified this circuit a little bit in a way that actually really enhances these errors, but makes them theoretically easier to subtract off, then we can estimate that the intrinsic fidelity of the gate is around 99%, plus or minus 2%, which is to say, very good. So because it's very good, we would like to make a more precise measurement of how good it is. So we do that using an approach that's very similar to what I showed you for single qubit gates, again, called randomized benchmarking, where we now run a circuit that consists of single qubit gates and 2-qubit gates in sort of an alternating sandwich structure, but where the single qubit gates are randomized. And they basically rotate the state around through Hilbert space in a random way, such that the probability that you return to the correct state at the end as a function of the depth of this circuit tells you something about the intrinsic error of the 2-qubit gate. And so from this decay here, we see that the error per gate for this 2-qubit gate is about 98%, which actually would have been the world record gate for Rydberg atoms, if not for this very nice paper from the Lukin group at Harvard a few months before, or about a month before this. And we understand roughly what these errors come from, and it's a little bit the Rydberg lifetime that we're not doing the gates fast enough, a little bit Doppler shifts and other. But I think there's a clear prospect to improve this, probably at least another order of magnitude. However, the important thing that we wanted to demonstrate about this metastable qubit is that we can see the errors when they happen. And so the way we do that is by, it's a little different from what we originally proposed. We just wait at the end of the gate, we just wait to let any population that is stranded in the Rydberg states decay back down to the atomic ground state. And then we detect that together with population that decayed there immediately. And when we do the same kind of benchmarking with this mid-circuit erasure detections that we did before, we see that by removing the cases where we saw an error happen mid-circuit, we can improve the fidelity from 98 to 98.7%, thereby converting about a third of the errors into erasures. So this is not as high as you can fundamentally do, but we have a clear understanding of what sets this limit now. So I've got just 2 more slides. So the nice direction I think that this work sets forward for the field of quantum computing is, I think, for a long time, people have only worried about basically the gate fidelity. You've got to decrease the gate error probability to get below the threshold, and then keep decreasing it to get further below the threshold so that you can do better and better error correction. And what this idea of erasure conversion opens up is that if you actually want to minimize this logical error rate, you shouldn't worry only about the error probability of your qubits, you should also worry about the threshold. And that by engineering these qubits so that a larger and larger fraction of the errors are erasure errors, we can also increase this threshold. So now we have 2 different axes to engineer on. 1, make the gates better. 2, make the erasure fraction higher to increase the threshold. So now we have pretty clear understandings of how to do both of these things by changing some technical things about the experiment, making the gates faster, better lasers, and so on and so on. I'll skip this slide, but then the last thing I want to say is that, one of the things that's really exciting about quantum computing as a field, which I'm sure you will get a sense of from these talks, is that there's so many different approaches, so many different ways that people are working on quantum computing. And while they might seem very different, what do quantum dots have to do with superconductors, have to do with trapped ions and neutral atoms? In many ways, there's a lot of commonality, and many of the best ideas in the field have come from, exchange between different platforms, or somebody in, neutral atoms being jealous of how well superconducting qubits work and trying to think about how to steal their ideas and so on. So in that spirit, one thing that I'm sort of pleased to see is that this idea of engineering qubits that have predominantly erasure errors has been explored now by other authors in the context of trapped ions and in the context of superconducting qubits in particular. And there's really nice experimental demonstration now from Rob Schollcroft's group at Yale on a new type of superconducting qubit they call a dual rail qubit that's exactly designed to convert the dominant errors into these erasure. This idea is actually not particular to quantum computing. You can also do the same thing with quantum simulation to try to correct errors that occur or detect errors that occur in quantum simulations. And Manuel Enders' group at Caltech has demonstrated that very nicely with strontium. So with that, I want to conclude with this picture of the very pretty colors of lasers we have in our labs, and thank these people who've worked in my group over the years on this project, and thank you for your attention.
Thank you very much, Jeff, for this great lecture. It really made us take a dive into a variety of topics in neutral atom quantum computing and more general. I will ask a couple of questions that emerged on the Zoom, and then I would like to review neutral atom computing, quantum computing with the DiVincenzo criteria with you for everyone to solidify their knowledge. The first question, a lot is happening in industry as well with neutral atoms, atom computing, Pascal, Quera. What is the main difference between their approaches?
Well, it's a little hard to say because I don't think that any of them would, I think they're all in their early days. So I don't think any of them know what their approaches are yet. At a high level, however, maybe I can say a few things. So, from what is publicly available, Pascal and Quera are doing a lot of work on kind of analog quantum optimization, things like that, whereas cold quanta and atom computing are a little more focused on digital quantum computing, gate-based quantum computing. But I'm sure that Pascal and Quera are thinking about that, pretty hard as well. Another major difference is that, again, based on what we know now, Quera and Pascal are working with alkali atoms like rubidium or cesium and cold quanta. I'm sorry. But then atom computing is working on alkaline earth atoms. They started with strontium, but now they're working on ytterbium qubits, like we showed here.
Miguel Gonzalez from Mexico asks, have you actually run a quantum algorithm in your lab?
No, so we're working on it right now, though.
Exciting. We might hear about that next year. Great. Then Erica from US. This technique really stands out because it is at room temperature and you use the lasers to cool to extremely low temperatures. Does this imply that it is more energy efficient than, for example, superconducting qubits that need to be cooled with a solution refrigerator? Maybe, but I wouldn't. I wouldn't bet on it. I think one has to think very carefully about all of these error budgets and the electronics in all cases, or all these energy budgets. I'm sorry, and the electronics in all cases are a big fraction of the energy. So I'm not totally sure. Yeah, and you have all the lasers, and I will briefly take over screen sharing and
sure.
Return to the DiVincenzo criteria. Could you walk us through again and give a summary on all of these, who it works for, neutral atom quantum computing, as a summary for everyone?
Sure. Yeah. And when I teach, I teach a class here for first year graduate students where we cover all of the different quantum computing technologies, and this class is organized the same way around. For each one we talk about the DiVincenzo criterion. The scalable, the qubit is the electron or nuclear spin of a single atom. I think what exactly scalable means in this sentence is one of the most debated points of the DiVincenzo criterion. But let me point out that we can buy 10 to the 23 of these ytterbium atoms for like $4. So they're very cheap. Second, the ability to initialize the state of the qubits to a simple fiducial state. So for us, in general, the way you do this with atomic qubits is with optical pumping. So you sort of apply a polarized laser and you basically transfer the angular momentum of the laser into the spin or something and prepare it in a well-defined state. For the case of our metastable state, we also have to get the qubit out of the ground state into that metastable state, but we also do that with optical pumping. The third is long relevance coherence time. So this is something that's not generally an issue for atomic, like trapped atoms, trapped ions, and neutral atom qubits. These atomic systems, because there's not a noisy solid state environment, have coherence times in the seconds, basically for free. The fourth is a universal set of quantum gates. So I showed you that in our talk, single qubit rotations with a magnetic field and 2 qubit gates via the Rydberg state. Another thing that's an important part of universality for a large computer is not only that you can do these gates, but that you can do them in a locally addressed way. So I can do a single qubit rotation, on this qubit, or a 2 qubit gate on these 2. That's something that's actually been a little bit more of a challenge for atom and ion qubits compared to superconducting qubits, say in quantum dots, because we don't have wires that are attached to the qubit. So you have to do this with focused laser beams. But the physics of how to do it is pretty clear, but actually the engineering of generating a whole bunch of focused laser beams is hard, but something that people are making a lot of progress on, and we're working on too. And then the fifth is measurement, and I showed you that too. We take a picture of fluorescence emitted from the atoms. And one thing that's really nice about doing that is that we can take advantage of things like cameras that already exist, right? I showed you a picture in my talk of 400 or of a 400 site array with like 200 atoms in it. That wasn't a qubit measurement, but it could very well have been. Let me go on to these last 2 points here because they're kind of interesting. I think something that's going to be a big challenge for any quantum platform is if you're going to go from tens or hundreds of qubits to tens of millions of qubits. Probably you're going to have to split them up between different modules that might sit in different parts of a room or even different buildings. And to get information from one module to another is going to be hard because you're going to have to leave like your cryostat, for example, or your vacuum chamber. So one thing that's really nice about atomic qubits, by which I mean trapped atoms or neutral atoms or trapped ions, is that we know really very well how to entangle the quantum states of those atoms with photons that we can then send over optical fibers over pretty long distances. So that's not something that I would say has been done yet in with a rate or a fidelity that's really compatible with scalable quantum computing, but it's another exciting frontier in this area.
Excellent. And to conclude, which literature do you recommend for the people for whom it is new, but also for the more advanced, to learn more about neutral atom quantum computing? Well,
so assuming this talk was recorded, I think I had references on maybe the first 10 slides or so to a couple of review papers and important seminal papers in the field that I think you could look at.
Fantastic. Thank you very much, Jeff. It was really a great pleasure having you here, and you introduced us to many topics. Thank you very much. And this was an inspiration to everyone to take it further in neutral atom quantum computing.
Yep, thank you very much. It was a pleasure to be here, and I hope the rest of this workshop is exciting for all of you. Goodbye.
Thank you very much. That brings an end to the 2 lectures of today, not an end to the session. We will have a variety of WOMANIUM team members on to share more about their research topics with you, which range from quantum optics and lasers to trapped ions to art about physics and quantum materials. But first, a well-deserved break. We will have a break until 6:30 ET, 13 minutes, and then continue with all the team spotlights. And during the break, we will keep chatting a bit, but feel free to take it easy. In the meantime, team members Heisa and Madalena came online. You, together with Alex, organized the hardware lectures. Can you share more about the highlights of the upcoming weeks? What do you think will the highlights be, Madalena?
Hi, I'm not sure if Raisa wants to go first.
Okay, let's do it together. Yes, we will have this week will be full of hardware lectures and virtual lab tours. And I am looking forward in reality to the first lab tour that will be from IQM on Wednesday. Yay! I don't know if all of you know already, I'm an experimentalist, so everything that is related to labs, I'm quite happy with it. But we also have amazing keynote speakers this week. I think we'll have a photonic quantum computing coming up soon on Friday, and this will keep going the next weeks as well, right? And Friday as well, we'll have a virtual lab tour at DTU, that is the Technical University of Denmark, and you'll be able to see how does a photonic quantum computer looks like as well. So to be an exciting week for hardware.
Yeah, and what will be really great is that there are a variety of lab tours in companies. This is pretty unique. Usually academic labs are more open to sharing their labs, but here on video, we will have company lab tours for you. Not all will be available in the recording, so we encourage everyone to join the live sessions. Can you share more about the highlights, Madalena, in your opinion?
Yeah, of course. I think the really cool thing that we do in this program is that we allocate one lecture for all of the main hardwares for quantum computing. I think when it comes to hardware, things become a bit more complicated because every single hardware has its own advantages and it has its own disadvantages. You need different types of skills to work with all of them. And I think it's really nice to see people who are very knowledgeable and are at the top of their field in these hardware, in these types of hardware, and they come to speak to us and present them so that we can see all of them and kind of compare, see which one we think is going to be quote unquote the winner of this quantum race. Maybe we will just use some of them for certain applications and some of them for others. And I also think it's pretty cool because when I started my quantum journey, it was kind of hard to decide which one I wanted to lean towards. So I think it will be a really great experience to have an insight into all of them and be able to compare.
I fully agree with you. Your audio, by the way, Madalena, is a bit disturbed, so please try to fix it before we have more questions to you.
Of course.
And a couple of people just gave compliments about this GIF, and these kudos go, all of them, to Anthea, one of our art and design team members, who is a specialist in art and design, but now has been introduced to quantum topics like Schrödinger's cat and designed this for everyone. Soon also Karina, our team member, is on, who makes many beautiful illustrations, and we'll share more about that. Back to you, Haisa.
Sure. No, I'd just like to say that there is a question in Scott. So when we have the lab tours, yes, when you see people walk around the labs and showing the hardware, so you have really an experience of how a lab looks from inside, and also what people is doing there. So I would say, as Malu said, some of these lab tours will not be available afterwards. It's very important that if you can, you join online and participate in it, right? So you will have people answer your questions afterwards. So there will be like a live Q&A session after the virtual lab tour. Yes. And I think also some of you before asked about how to start for hardware, right? When you have like, how do you learn about hardware in general? I would say that most of it comes with experience, but also reading papers, right? There is not as many books like teaching how do you work in the lab, but when you read review papers, you have a good idea. And also when you are working in the field, talking with people is the way that you learn the most about the practical things in the laboratory. Yes, I don't know if Malu has more tips to share.
I agree with you, and you also cannot understand or know everything at once. For example, to understand everything that Jeff told, you really need to know a lot of physics, yeah, you need to know all that basics and even to some advanced level. So take away what is appropriate for your level. You know now that that Rydberg atoms play an important role, for example, and take this as a basis to talk more with people, to read more. You will see that the quiz about this topic is more basic. It will ensure that you know how the DiVincenzo criteria are implemented for this modality. And that we would really love for you to know for all the different qubit modalities. How do the basics work? And then, in addition, we hope to inspire you for these more advanced topics. How does error correction really work with for this implementation of quantum computing and others? But we understand that for all different levels in the course present, you will take something different away from the lectures. Yes, and we have a break right now, and in 5 minutes we will continue with half an hour WOMANIUM quantum spotlights. Hussein from Lebanon suggests learning atomic physics for this lecture. That will help a lot. I agree with you, Hussein. Atomic physics for the neutral atom, while for superconducting qubits you actually need different background again. And this series also has the purpose to give you some broad orientation for you to see what would you like to learn about more. And then you can dive more deeply into it from there. Other team members, if you are available, please turn on your video and Lindsay will spotlight you and you can be included in the conversation. Varda from India asks, what are the prerequisites for the next hardware lecture? Would you like to comment on that, Haisa?
Yes, I'm seeing that the schedule. The next hardware lecture will be superconducting quantum computing. So I would say if you have like if you didn't have any contact with it, try to look in the main website, right? To have an idea what it is, how does it work. Don't need to go too deep, just like to have a good idea of how things work in superconducting qubits, and you'll be at least prepared for the lecture. From last year's program, we had a lecture from MIT, right, on superconducting qubits, and you can also check in the website, in the YouTube channel, to be prepared. But I think the important part is to join the lecture. So you hear more, the lecture will be structured to make everybody try to understand the main concepts. Yes, and afterwards you know more about it.
Yeah, and please give it some thoughts. What are the basic concepts? For example, first of all, the two-level system. We can use real atoms for that, or we can use artificial atoms for that. And how do we realize these systems artificially? With superconducting qubits, superconducting circuits, that is an entirely different way. Sarah from Italy asks, will the bootcamps be recorded? The answer is yes, we will keep recording and they will be posted usually within a day on the YouTube channel. The bootcamps have an important part that you also work on the problems yourself along the way. So it is very beneficial that you're there in the live session, and there will be breaks for questions very often.
Yes, maybe just to share in the last 2 minutes a bit more about the hardware. It's very important that you have you learn different concepts, right? Like electronics, coding. So keep in mind that all of it, if you know it already, it's already like a good step forward to the experiment. So most of the time you're doing optics, lasers, electronics, mechanics. It's a variety of subjects that you work at the same time. And all of these skills, if you have already, they will be important while you are doing your experiment. So I see Madalena doing like this. It's like it's a common thing that we share, right? We need to do different things while building the experiment. So yes, keep in mind it's like electronics, mechanics, yes, and the different kind of knowledge that are around the hardware.
Could I add just a little bit? Can you hear me well now? Is my microphone
Yes.
okay?
Thanks for fixing that.
Great.
Great.
I also wanted to say that you don't have to know everything. I certainly don't know how every single piece of equipment works in my lab. But the thing is, if I encounter a problem with it, there's always a manual, there are always forums. And I think on top of knowing like exactly how stuff works, you need to have this mentality of how do I solve a problem? If I encounter a problem, how do I solve it? And these are skills that will help you no matter what job you're doing. They're called soft skills, and you kind of need to learn it. And I think with this program, we're not trying to have like, you don't need to be like an expert in trap time, quantum computing, or in photonics, but we're trying to present you what is out there and hopefully encourage you to go and look for more. And then maybe after this, and maybe especially because we have a career fair at the end, you kind of start with the knowledge that you have, you build up on it, and then you can find a job. You can kind of pursue your career by joining the university, doing a degree, or doing a further degree. Maybe you already have one. So yeah, I wouldn't panic if you have lectures and you don't necessarily understand everything. I would just take this opportunity to like make a note, go look for it, and then this kind of develops your skill of doing research, because that's basically what we're doing. We're exploring what we don't know.
Right, and it should be a launchpad for everything. Even if you ask a superconducting qubit expert about trapped ions, often their answer is, no, I'm a superconducting qubit expert. I know nothing about trapped ions. After this course, you will know a little bit about everything, which will already make you very unique. It is 30. We'll start with the team spotlights. Welcome back, everyone. I hope you had a little bit of a break. And now I would like to ask the team, Karina, Akshita, Ananya, to also turn on your video. We started WOMANIUM Quantum last year in early 2022 with the founders of WOMANIUM and myself. And soon it became very popular among industry partners, among participants, and we rapidly expanded the team. With people who joined very early were Lindsay, Haisa, soon Alex, soon Madalena. And meanwhile, many people also from last year's program joined the team, which has been an amazing experience the past year to organize everything together. And here you see a brief overview of all the wonderful team members who work in quantum themselves or study quantum themselves, or topics that are also really needed, like more a focus on promotion or artwork. And I would like to start with that very topic. First some art and then some physics. Karina, you are the one who animated all, let me see if there is some, here in the right top corner, who create all of these images. Could you share a bit more about your background, how it is to create physics art, and about your inspiration?
Yeah, sure. Would it be okay if I shared my screen?
Yes, we want to know everything about you and about how to make physics and art so great together.
Okay. Hi, so my name is Karina, and I am one of WOMANIUM's designers, and I've helped create a few of the promotional media you might have seen already, such as speaker banners and also the designs on the slides. I graduated from Art Center with a BFA in illustration, and I'm planning to go back to school for my master's in graphic design. But for the next few minutes, I'm going to share a few personal pieces from my portfolio. My personal illustration style has somewhat of like a childlike quality to it. It's like something you'd see in children's books. So starting off with my February illustration, I was inspired by the Valentine's candy hearts colors. and I wanted to draw a couple walking in the garden. So with that, I made a pastel Valentine themed landscape. And for my fall illustration, it's pretty straightforward, but I wanted to draw like a cozy outdoors autumn atmosphere by incorporating colors that we would associate with fall. And these two pieces are from my graduation project. There are travel posters based on tourist spots and activities that you can do in the country of Taiwan. And for this piece, I did use more of a graphic shape approach, but I did incorporate some of my own style into it. And for patterns and surface design, I did a children's pattern collection with an underwater animal theme. And since I intended to like market it towards children and babies, I placed my pattern on a wall mock-up of a children's room. And for this collection, I used flowers and weddings as my main inspiration. So I created like a spring themed floral collection to be used for weddings. So I found mock-ups of goodie bags and wedding invites and placed my patterns onto them. And for my final collection, I did fall themed patterns inspired by colors you associate with fall. And then I placed them onto notebooks and created a fall themed collection. But yeah, that's the end. And thank you for letting me present a little bit of my work as an artist.
Can you share, Karina, something that might be familiar for everyone is a creative block, either in art or in writing? How do you overcome creative blocks?
Creative blocks? I would just step away from my work. I think that's the best advice I was given when I was going through an artist's block in college, was to just like step away from my work, to do a hobby, to go on a walk, to do whatever, and like just come back to it later. Because sometimes when you're focused on your work for too long, you can't like pick out what you can see or, edit, fix, take out. So yeah, I'd say just step away from your work, take a bit of time for yourself and just come back to it later.
Then a technical question, what is the main software you use?
I mainly use Adobe Photoshop, and I also use Procreate on the iPad.
Fabrizio from Mexico asks, yeah, and indeed Procreate, Natalia. Fabrizio from Mexico asks, what do you think about using AI to do these artworks?
I don't have much of an opinion on it yet, but I think I've heard a couple of studios incorporating it already with a few of their movies. But I think like as long as you make sure to work with artists and AI, I think it could work pretty well instead of just using solely AI.
Thank you very much for sharing that, Karina. And we are very excited to soon release the new quantum emoji illustration package. Those will soon be on Discord and all prepared by Karina. Our next team member is Akshita, and she, together with colleague Tanek, won the Quantum Hackathon last year and has since then been developing their QML models for cancer diagnostics. Akshita, could you share more about that?
Yeah, thank you for the introduction. Hi, everyone. I'm a high school senior right now, so I'm not like professionally in the quantum field yet, but it's just something I've gotten in through my school. And so here, let me share my screen so I can show my slides.
And this is also to point out, we had all different levels in last year's program, and this year again, including industry professionals, including professors, postdocs, but also very bright and enthusiastic high school students who might then be the winners of the hackathon, like Akshita. Please share your screen.
Yep. Okay, it's loading. Can you all see my screen?
Yes, we can.
Okay,
No,
perfect.
but
Just loading.
please go ahead.
Yeah, that load.
Yeah, just start presenting like this otherwise.
Perfect.
I think you can do it without slides, Akshita.
Okay.
Let's go.
Yeah, this is. Oh.
Please just go ahead. You don't even need
Yeah.
them.
Let me get out of the slide thing.
So what is business as usual, Akshita? What are you looking into?
So basically, it's looking at a quantum machine learning model. And the goal of our model is to basically just predict the life expectancy of a patient with a specific type of cancer. And looks like my slides are good now. So I'll just go through it like this. And so while this is loading, let me just give a verbal talk because the slides kind of go through what I'm talking about. But basically, our major issue here was that 25% of all cancer in the United States comes from lung cancer. And so that's kind of why we decided to focus on it. And so the big problem here is that right now, when oncologists, they make these lifespan predictions, they use the generalized research studies. So if there's a common group with a common symptom, then they kind of group that together instead of looking at someone's personal records. And so this causes an issue and it has an error of a year, as you can see on the slides. And so that was our goal, to kind of come up with a personalized model to be able to approach this. And we decided to use quantum computing for this because when it comes to clinical data and we're dealing with real patients, it's much easier for quantum machine learning to be able to handle that noisy data rather than classical machine learning, which is not really able to fit a function to that data. And so after doing our preliminary research, all the stuff on the slide here is just a bunch of technical stuff, but I'll just explain it as I would explain it to anyone else. But basically, the way that I like to think about it is that we take these data points for patients and then we try to encode them into quantum states. And that's what kind of the quantum computing aspect of this is. And so we used regular pre-processing, and then we put the data points into the quantum state. And that was through embedding templates. And so basically what embedding templates do is that they put they put data points into these different states. And the reason why we use that is that we can plug it into a support vector classifier. And all that does is give us an accuracy. So the big gist of our project here was that we had classical machine learning models and we had a quantum machine learning model, and then we compared the two using the same data set. And so we found that our quantum classifier had a 37% accuracy, while the classical equivalent was just 4%. And so that was really inspiring to see quantum machine learning and quantum computing having a much efficient and more effective solution than classical machine learning. And so we think that this has a really big projected demand. I think as we all are here knowing that quantum computing has a really big potential in the future, and there's so many different applications of it, I think it's really exciting how we can reduce the human error and have a more personalized recommendation and just better the quality of life for these patients who are already going through a stressful time. And yeah, so currently we're just working on expanding into other types of cancer, and I'm looking into doing other projects in quantum machine learning. But yeah, thank you for listening.
Akshita, Otmane from Morocco asks, if someone wants to learn QML, should they first be familiar with classical machine learning?
Yeah, so currently I'm trying to get deeper into quantum machine learning myself. And so what I'm doing is I'm taking an online course about classical machine learning and adjacently doing one on quantum machine learning. And I think it's really helpful to see how those two connect, and it's just better to do both. Yeah.
Then what are the benefits of quantum machine learning over classical machine learning? What is really the crux there?
Yeah, so I was explaining, I think in general, the biggest thing for me personally that I found quantum machine learning was statistically better for is that when we have patient data, when we're dealing with any data where it's like real people and it's like clinical data, for example, the data itself, there's a lot of points missing, and a lot of the data just isn't fitting like a very structural format. And so classical machine learning works really well when there's a really nice, good data set that you're working with. But if you're working with a clinical data set or data sets where there's a lot of points missing or it's just noisy overall, then I think quantum machine learning is just better in that case.
Could you suggest some QML books? Let's leave this question on Discord, and you can answer there, Akshita. And What are your plans with this? Laurens from Netherlands asks, what companies are you aiming for to bring your model into the attention of industry?
Yeah, so we've actually been working with the WOMANIUM team for about a year now because after winning the startup competition from last year, we've had like bi-weekly meetings to actually turn this into our own company. So the current thing was just doing outreach and talking ourselves to people who we could potentially bring this idea to, but we've just been working on it ourselves to try to bring it to our own company.
Excellent. Then there are some more technical questions. Please continue answering on Discord. Akshida, thank you very much for sharing this exciting project with us, which we hope will really give a benefit in the future.
Of course, thank you.
Moving to some hardware topics. Madalina, could you share about the world of trapped ion quantum computing and what is it like in the daily life of a PhD researcher?
Of course, let me share my screen as well. I made a little presentation. Let me know if you can see the screen.
Yes.
Perfect.
Not in full.
Yes, I will put it in. Okay. Yes.
There we go. Quantum hide and seek, the experimentalist experience, what to do when things go wrong, which is often. Go ahead.
Yes, hello, my name is Madalina. I am originally from Romania, and I came a few years ago to the UK where I did my bachelor's and master's in physics, and then now I am doing my PhD in trapped ion quantum computing. I am an experimentalist, which means that I really like to basically learn about the theory, but I really like to get my hands dirty and like touch stuff, move stuff, and actually see quantum come alive. And in this little, it's a very, very short presentation. I just wanted to show you a little bit of kind of the problems that we're encountering in the lab, problems probably that are a little bit general to quantum computing in general, and maybe some of the things that we are using to solve them. It will be a little bit technical, but don't worry if you don't understand what I'm saying. I will kind of summarize everything at the end, and you can ask me questions on Discord. So quantum hide and seek. And I called it like this because sometimes it feels like quantum is still hiding under classical when we're trying to do quantum computing. And this is one of the, I would say, one of the main struggles that we have, that everybody that works on quantum hardware has. So what do we need for quantum computing and actually for science in general? You need a theoretical model. So the one that you see there is is a phase-space diagram of the gate that we are doing. And then you need an experimental setup. So this is a diagram of the experimental setup, just to give you an idea of how many different things go into having a quantum computer, driving it and using it. And then in order to do this, you need to have repeatable good results. So we heard that we need 99.999 at least % fidelity gates to be able to have error correction and do good and like large scale quantum computation. However, all of these, the theoretical models are hidden under approximations because we can't properly simulate all of this. And then the experimental setup is hidden under parameter drift and noise. As you can see in the measurements that I'm showing you, those are like real measurements from our lab. We measure them in a cable. So then what is the solution? What can we do about this? And what I'm trying to do through my project to kind of solve and find these quantum effects underneath these problems. So for the theoretical one, to kind of solve the approximations, we can use experimental results to improve the simulations. And one of the ways we can do this is using Bayesian optimization. For people who do machine learning, they know that Bayesian optimization is some sort of machine learning, and we know that it uses a model that it keeps optimizing by using experimental results to arrive to the correct solution, as you saw here. I'm going to go again over that. Yeah, so you see that it's searching the landscape and it kind of arrives at the good solution. So we just kind of take the solution, we put it as parameters into our computer, into our quantum computer, and the gate should work better. For the experimental setup, we have two different things. So for parameter drift, you can do fast calibration and use automations. For this, we use a direct acyclic graph. I know this doesn't mean a lot to a lot of people, but if you have a computer science background, you probably know what I'm talking about. And just to give you an idea, these are all the parameters that we have to optimize before we can even do a gate and get a high fidelity gate. And then the last one is to do smart control of the pulses that we are applying to the gate. So this is called dynamical decoupling, and it involves a couple of different things, which I'm not going to go into because I think they're all a bit too technical. So 8, 9, 10, where is the gate? For my project currently, the gate is still a bit hidden by noise, which is why what I'm currently doing is working on hardware. Specifically, we are trying to improve a filter to filter out more noise. But what I wanted you to get from all of this is that quantum computing needs a lot of talent. You heard me mention computer science, you heard me mention classical machine learning, you probably didn't, but we use lasers, we use electrical setup. So we don't just need physicists, we need engineers, we need computer scientists, we need so many people. And yeah, this is just to kind of show that the theoretical modeling goes into the pulse design modeling, and the experimental setup kind of combines with the theory to give us a better model of how we can do gates. Thank you.
You work closely with a startup company as well. Could you give us some idea? What is a team typically comprised of? Is it indeed also electrical engineers, computer scientists? What is the reality?
Yes. So I am mostly in the lab. So I don't have a lot of contact with the company. What I will say though is that in the lab, you are in control of your own experiment. So if a laser breaks, you have to fix it. There are some technical people to help you, but not really. Whereas because I work in collaboration with Universal Quantum, I can go to them and be like, hey, I know you have an electrical engineer that has done a degree in electrical engineering, and they can help us with this. For example, the filter project that I told you we're currently working on, we are working in collaboration with UQ. And I don't think just using the research from the university, we would be able to do that, because the research group is quite small, and kind of as a researcher, you're trying to do as much as possible. But in a company, you have a specific role, and I think that's really nice because you know exactly what you're doing and you can go really deep into everything. Whereas I feel like I know a little bit of everything and I'm trying to do my best.
That is often really an asset of experimentalists. The critical thinking, the troubleshooting, and needing to know a bit about everything to execute that well. Indeed, fix some electrical circuit, fix a laser, do at least that first troubleshooting yourself, and then decide if you can also fully fix it yourself or ask the company or others. Natalia from Bolivia asks, Madalena, do you have some advice for PhD applications in physics?
I mean, I think for a PhD, sorry?
And what is the best way towards a PhD? Should you do research as an undergraduate?
From my own experience, I've not done quantum research as an undergrad. My master's was actually in particle physics. So I worked at CERN before I did this PhD. If you're not sure, look for something called a CDT, of Center of Doctoral Training, which is what I'm doing, where basically the master's is combined with a PhD. So you have a little bit less time for your PhD, but you do this preliminary master's, which covers all of the topics. Is basically something similar to what WOMANIUM does, but done by a university, where they cover different topics so you have a better idea of what to do as a project. For the PhD, I would say, yes, definitely do some research. Figure out what you like. Is it theory? Is it experimental? Figure out what kind of hardware do you like if you want experimental. And then it is really important to try to contact people who are already in the group, who are already doing a PhD there, to ask them, how are the professors? Are they involved in the research? Are they not involved in the research? Which one do you prefer? Do you prefer your professor to kind of micromanage you, or do you prefer to have the free reins? I think the PhD is definitely a unique experience. And I would definitely say do a bit of research and talk to the people that work there. Try to find their emails. Usually research groups have emails online. Try to find emails, send a couple of emails. I'm not saying that everybody will respond, but I'm pretty sure that some people will do.
Great advice, Madalena. Azuana Mila from Mexico asks, after your PhD, do you plan to continue in academia or go to a company?
I think I would prefer to go to a company. I think in academia, even as you progress, you still kind of spread yourself a bit thin and do a bit of everything. And I would like to have my own project and just kind of drive that forward. And I think you can do that much better in industry than in academia.
Why did you shift from high energy physics to quantum computing? Asks Mohammed Reza from Iran.
So I really liked quantum computing, but my undergraduate university wasn't offering a lot of courses on it. So I went for what they were offering, which was particle physics. I don't want to offend anybody who's doing particle physics because I think it's really interesting. But when I did it, it was a lot of data analysis, and I didn't really enjoy that. And I think when the accelerator is not working, there is a lot of data analysis, there is a lot of engineering that goes into it. And because the collider is so big, as David DiVincenzo said this morning, there's a lot going into it. It means that you're doing a small part in a bigger project, whereas I like to be in charge of my project. I like to have my experiment with like 2 or 3 other people, and we are driving it. We're saying what gets done, what experiments we're doing. Whereas if you work for CERN or Fermilab, I think that's a bit harder to do.
Last question to answer fast. What is your typical day? Is it mostly experiments? Do you also do simulation? Do you also do analysis?
I think it really depends. I have days when I do 9 to 5. I have days when I do 9 to 10 p.m. And there are weeks where I have a list of to do and something breaks and half of that list doesn't get done because you need to be in the lab facing it. So I really couldn't say a typical day, but I would say that it keeps you on your toes and you never get bored. So that's really interesting.
Wonderful. Thank you, Madalena. And there are more questions to answer on Discord. The question about doing a PhD really comes very often. And first, please ask yourself, do you need to do a PhD? For many jobs, it is not necessary. So what is your end goal? Because it takes almost 5 years. How do you want to spend that time? And does it lead to your end goal? 2, if you do a PhD, pick your advisor really well. Your advisor can really be the key to success or no success. And 3, in different countries, PhDs are very different. In some, you are paid a salary and you even build for your pension. In others, the durations vary. And also, in some, you are working on your topic right away, while in others, you have some rotations on various topics. Feel free also to ask about that in the chat, because there are many PhDs in the group. Ananya, how is your internet connection? Can you share about your AI chatbot? Ananya's internet is not the best. Then we go to Vardan, because there was already a question, how to win hackathons, and you are still the best to answer. And then share a bit more what you are currently interested in.
Sure. Yeah, how to win hackathons? I said it before, have fun, enjoy, and participate in as many hackathons as you can. What I have been doing so far, I prepared some slides. I would like to share my screen. Just let me know when it's visible.
Yes, it's visible.
Perfect. Hi everyone. First of all, I hope you're enjoying the WOMANIUM program so far, and there are a lot of exciting things coming. So yeah, please stay tuned for that. A lot of you have already connected with me on Discord and LinkedIn, but for those who do not know me, my name is Vardhan, and I'm currently leading the software team at WOMANIUM, and I'm also heading the Quantum Solutions Launchpad, which is a very, very, very exciting program which we have designed for you, where we would be selecting the best candidates out of you all to work on real-world industrial projects. About me, in the past, I've been working as a quantum developer and a quantum, I would say, researcher at various academic institutes and at companies as well, like Tata Consultancy, ISA Kolkata, and many more. And along the way, I have actually contributed to more than 20 quantum open source projects, which is, again, I would say, a really good way to hone your skills and show your skills to the public, because open source projects are really valued by the companies as well when they're hiring. So I would advise anyone who is looking to step into the industry to try doing those. Apart from that, as many of you already know, that I have been participating in a lot of hackathons. And over the course of, I would say, last couple of years, I've more than like a dozen hackathon wins. So yeah, that is one thing. How to win a hackathons? Once again, have fun while doing the hackathons. You do not need to win every hackathon, but you need to learn during every hackathon. It's not like if you do not win, you do not gain anything. You would always gain some experience. You would always gain some knowledge. And most of all, you would get some connections built during that time you are participating in a hackathon. So for today, I've actually shortlisted a couple of my projects which I wanted to share with you. And these are some projects, some recent projects, and these are high-level projects which I wanted to share and give you a basic feel of what is happening in the industry right now. So the first one is in the optimization domain, where quantum computing was used. And this was like one of my most recent projects. It was, in fact, completed only a couple of months ago in collaboration with NPL. NPL, for those of you who do not know, is one of the largest scientific organizations based in India, and it keeps tracks of all the measurements and scientific standards across the country. It is, I would say, very similar to what NIST is in the US. It's a kind of an analog in India. So National Physical Laboratory is somewhat same as NIST in the US. And what I did was, in this project was, I tried to optimize the placement of PMUs across the energy grids across the country of India. Okay, so a little background, what PMUs are. PMUs basically stand for phasor measurement units, and they're installed onto power grids and energy grids to record and analyze various electrical stuff in the most trivial sense. And okay, so what is its use? What does PMU provide us? What does it analyze? A couple of you might relate with me, especially those who come from India, that a decade back, power cutoffs were really, really common in India. Like anytime power would just go out, no electricity in houses, and that was really, really a bummer. But nowadays, these power cuts are really rare. Like once in a blue moon, you see a power cut, and that is also something like really, really rare. The reason why these power cuts have become less, one of the major reasons is due to the placement of these PMUs upon the energy grids. So what is this problem basically stands is that, as you can see on the right hand of the map of India, there are a lot places where PMUs could be placed. Ideally, you would want to place them in all these locations, but according to the budget, it is not feasible to place them in all. So my role was to try and optimize and get with the best possible solution, the most efficient points, where placing the PMUs could result in a better manner. And a funny thing was that once I completed the project, I realized that the budget of this organization, NPL, just got boosted, and my solution was no longer required because now the budget can actually cover all the potential points on the country. So essentially, there's no need for optimization. But nevertheless, I learned a lot during this project. And this is basically an optimization project. So if you are working in an industry, I think optimization or logistics is bound to be one of the key roles in any kind of an organization. So quantum computing can essentially help in that. There was another project which I completed a couple of months back, and this is really close to my heart because honestly, I did not do this project. I was actually a mentor, and students like you in the participants did this project. This was actually one of hackathons. It was early this year. It was at the NYUAD Quantum Computing Hackathon, where I was mentoring a team, and a team full of students. Some were high school students, some were graduates. It was a really, really good team. And what we did was we designed a quantum classifier for categorizing MRI scan images to improve the efficiency of Alzheimer's disease. And if you know that Alzheimer's disease is a really, really, I would say, severe disease, which is prevalent in old ages. But the problem is that there's no known cure for Alzheimer's yet. And the only way to, I would say, prevent Alzheimer's is to actually stop it at an early stage. So what we did was we designed this classifier where we would feed in the MRI scans to a quantum classifier machine. It would just separate out whether the scan is an MRI scan is a healthy image of a brain or it's an Alzheimer's affected, it's a diseased brain. And once we do that, it just helps the doctors to analyze the brain images faster and more efficiently. So yeah, this was a great project. And yeah, these were the two projects I wanted to talk about. And finally, I actually wanted to give you all some tasks. I know that you are all very busy with all the tasks of the WOMANIUM program as well, but there are two problems which I would like for all of you to try. These are very, very small projects. These are very simple projects. I discussed one of them last year as well. Yeah, so I've actually linked the GitHub links as well. So you could just replicate my projects and do them again. But these are some really, really fun projects because not only do they tell you how to use quantum computing, they also teach you some sort of a quantum phenomena along the way. The first one is trying to simulate quantum tunneling on quantum computers. And to do this, it's a really simple algorithm. It's just a couple of steps, and you can actually simulate how a Hamiltonian gets evolved with respect to time in real time. And that visualization is really good for understanding the quantum tunneling effect, which is really important speaking from a physics perspective. And the second one is based on the quantum image processing. Over here, I used a checkboard. So as you can see, the bottom images, the first one is a classical checkboard, black and white images. But once I try to encode that particular image and run it on a quantum hardware, a backend, you would see that the image is no longer a checkboard. It still has black and white images. It also has some sort of a gray area in between. But the images have gradually changed. This is not the same image which I started with. And this is a good visualization of how errors and noise actually affects the data which we are encoding onto quantum computers. So again, the FRQI algorithm used over here is really simple. You should learn that. But apart from learning the algorithm itself, you could also visualize how errors affect different backends, how noise is responsible for disturbing all the data we have on quantum computers these days. Yeah, so I guess that was it from my end. Thank you, everyone. For those who have already connected with me, please feel free to reach out to me regarding any of these projects. If you want to collaborate, I'm always open to that. If you want some guidance from me for your personal projects, again, I'm very happy to provide that. I've linked my LinkedIn over here. So yeah, please feel free to reach out.
Awesome, Vardan, and more questions are appearing on Discord. Please comment on the questions there, including about neural networks for the image processing.
Absolutely.
So we have 3 more team members to highlight, starting with Alex, who is a theorist on the hardware side, then Ananya about the AI chatbot, and last but not least, Heisa, our quantum optics physicist. Alex, what would you like to share with us today?
Hi, everyone. Wait, are you hearing me? Okay, it's nice. Yeah, I'm Alex Stefan Pietro. I'm from Cameroon, but a couple of years back, I moved to Italy, where I did my PhD at University of Salerno in the south of Italy. So basically, my PhD, I already spoke about that a lot here. Maybe let me briefly say some words and then we move. I will maybe show you what was it about technically.
Here with Heisa and Madelina, Alex has been responsible for organizing hardware lectures, virtual lab tours, further hardware topics, and the career fair that is coming up in three weeks.
So my PhD basically was based on using a Josephson junction that we already know. Maybe most of you know about that, to detect a single photon for axion dark matter experiment. So we started from a single Josephson junction. That's what I put here, from a single junction to a transport, because the work is still going on. We started with this Josephson junction, and now we are working with more quantum analysis here. And the work is done in collaboration at ENFN, where I will soon join as a research fellow. Okay, basically, this is the system we use first. That is the RLC, the Josephson junction, as we know, with the capacitance here and the resistance, and also this ion here represent the noise. So the idea is to detect this signal here when the noise is present, because we know, as Vardan or also Madalena mentioned, that the noise can, affect our detection, affect our system, so that we will not have some good result. So the idea was how to use this single junction using a classical approach. That's why I put this equation here. Some of you will not recognize this Hamiltonian here. So how to use the single Josephson junction to detect a signal when there is a noise. This is some of the results we got. So it was quite interesting because we were able to separate the noise. This is the classical approach I've said, to separate the noise from the signal through this, the DKC is statistical tools, the Kuma-Carroll index. Yeah, so we got some quite interesting result. And what we are working right now, working on the modeling, on the design of this the new system we are working on right now. Here, okay, maybe first here. As I mentioned here, we know that this is not realistic. If this model is not realistic, we are aware that to have some realistic model, we should have a Josephson junction coupled to a resonator. But in this case, first, we assume both are agile. That means the signal that comes here is directly injected into the system in form of this turn of current pulses, as we can see. But for these new cases that I'm working right now, so we actually put a complete set of the system, as we can see here. This is the transpond with a shunt capacitance here. And this capacitance here help to couple with the resonator, the LC resonator, and we have here the LC, the transmission line here. So basically the idea is to design and obtain some of the parameter also for the single photon, because we know this is in the dispersive regime. Here we have the dispersive shift, and with the dispersive shift, we can also have the number of photons that is in our system. So basically the work is still going on. Maybe very soon in the next event, I will be able to show you some of the results we got, because I'm working closely with experimentalists. I'm working with using Qtip, this quantum toolbox in Python, doing the simulation here, and soon we will compare the result with what the experimentalists in the lab did. Yeah, that's all. And as Marilu also mentioned, I'm working also at the hardware team in WOMANIUM program. So our goal was basically to define the curriculum of the program, of this program specifically, and also reach out to some potential partners and also companies, speakers, universities, professors. Yeah, that's what I was basically doing on WOMANIUM. Okay, that's all. Thanks.
Fantastic. Thank you, Alex. And during your PhD, you also did extremely interesting work on Josephson junctions as detectors, which are even of interest for the Department of Homeland Security. Please feel free to ask more questions to Alex on Discord, and he will answer them there. Then we have Ananya back, who is responsible for the promotion in the team. One of our team members who was part of WOMANIUM Quantum 2022. She will start as a freshman at Stevens Institute of Technology this fall. And you have done a variety of quantum projects, including an AI chatbot. Please share more with us.
Yeah, hi. Can everyone hear me?
Yep.
Okay, perfect. I'm going to share my screen. So I've been working on an AI chatbot since my senior year, and currently it's based off of classical machine learning, but as I'm part of
Your voice is breaking for me, Ananya. It is because, yes, please go ahead. No, we can't hear you, Ananya. Okay, we will do you can record one and post it on Discord, and then everyone will learn more about it. Then in the meantime, Haisa, please enlighten us. You're an expert in quantum optics from Brazil, did your postdoc at DTU, Technical University of Denmark, on squeezed lights for biological samples, and then moved to industry at NKT Photonics. Many lessons from you.
Yes. Sorry. Yes. Hi, everyone. So thank you, Malu, for introducing. Yes, I'm from Brazil, and today I live and work in Denmark. So I did my PhD in quantum optics, and it was a mix of theory and experiment in the domain of quantum entanglement. And from there, I started like this patient, what I would like to call towards the experimental part of physics. I think it's really fascinating, as Madalena said, how when you do an experiment, you can see the quantum physics working in the lab. So I'm kind of passionate for it. And I developed like sources to generate squeezed states or entangled states of the light. So what I will show to you today is not too deep in the physics. I will show you 2 pictures of the lab and also a project that I worked to promote quantum computing for young girls. Okay? And if you have questions about how it's to work in the lab, how it's to work in the industry, you can keep it, you can take it in the Discord channel. Let me just share my screen with you. So I should be able to see the screen here. Sorry, just a second.
At the end of the program, we will also see Heisa featured in the NKT Photonics lab tour.
Yes, and they think
and this is really crucial for various types of quantum computers. Now it is showing well, Heisa.
Is it showing well? Okay, good. So here, what you can see on this picture here on the left is a typical quantum optics lab. Okay, so here we are producing a squeezed light source to probe biological samples. And please don't get afraid with this table. It's you learn how to do it with time. So here we have our main laser source, and you have all of these optics around to shape the beam. And all of these, we have 2 main beams here, one in T64 and another in 532. This will come to this small component here. I don't know if you can notice it, but this is an optical cavity with a gain needle inside. And this one is the heart. So it's here that we produce the quantum states of light. So this is a squeezer. We are producing squeezed states here. We have some experiments going on this optical setup, but for these results that you can see here, I'm using this microscope. So what I was doing in one of the experiments was probing a cell, a THP1 cell, that is a cell of our immune system, using coherent light, that's the classical approach, like classical light, and squeezed states of light that has less noise. So I'm showing you a very noisy image here of a part of the cell, and we see that when we probe this cell with these quantum states, you have better definition. And with this, you can study the different components that are inside the cell, but not just it. Because of squeezed states, you are reducing your noise floor. You can use less power to have the same signal to noise rate as you are using. You can use less power and get the same signal to noise rate than using classical light. Okay, so if let's say that you need 1 milliwatt of power to get 2 times improvement, I'll just say numbers here. Okay, maybe you can use half of it and use the squeezed states of light, and you get the same improvement. And this is really important here in biology because 1 milliwatt is not a realistic number. In reality, people use much more, and this can damage the sample. So we would like to avoid it. And one of the ways is, for example, using this class of states. And another experiment that I did that I think was really cool, it was to probe the growth of bacteria using this mini incubator here. So inside it, we had a bacterial sample, and we are probing it using also classical and the quantum states of light, and seeing if you could detect the growth earlier. Because it's very important that when you are work with bacteria, right, as fast as you know if you have a bacteria in your medium and what kind of bacteria you have there, it's better for you. So this is another use of these states for probing biological samples. And you'll soon see it in our publication as well, and I'll put it on Discord when it's published. So these are different ways that you can integrate quantum and biology. And for doing these experiments, you kind of need to have a good knowledge on both sides. But you need to also have the collaboration of people that have a good understanding, in my case, in biology, because I'm not a biologist, I'm a quantum optics physicist. And also work together with people that has knowledge like in electronics and programming and so on. So it's a collaboration, and we do it together. So this is what I'd like to share about the technical part. And just to a part of WOMANIUM that I use a lot of my time, free time, collaborating with this amazing project. I'm also part of an organization that is called High Five Girls. And High Five Girls try to promote the field of STEM for young girls, so between 13 and 19 years old. So here you can see the website of the organization. And I asked, and together with them, we decided to do this quantum computing camp for these girls. So we had around 12, 13 girls in this camp. It's a 3-day camp. And what we do in the camp is to try to take a very a hard concept, break it in small pieces, and make it take the girls to try to learn the concepts and also to have fun with it and get the interest. So it was super nice to do this camp with them. I did it together with Ingrid. Ingrid is a data scientist and she's amazing. And Mariana here is the founder of High Five Girls. And we also had the collaboration of Matt. She's not in the picture. Unfortunately, she got sick on this day. And she's the one that helped us to take a very hard concept and break it in very small pieces that are understandable for young people, in this case, young girls. So here, just so you also to mention a fun fact here is this was a camp in English, but I am in Denmark. The girls, they speak English in reality, but in this day, I don't know why, they would like to speak more in Danish. So it was a conversation, both languages at the same time. So half in English from the part of us, and then answer and question in Danish. So it was quite a challenge day, but really fun day. So what we did, we need to break down the concepts of complexity of what a quantum computer is. And I'll share, there's a lot of slides here showing how a quantum computer works and so on. But we try to, for all the concepts that we developed, to bring a game to play with them. So here, for example, we are trying to teach them complexity. So they need to solve a problem and they need to find a way to solve it. In this case, they were blinded and just one of them didn't have a cover in their eyes. And they were trying to find the best route to go to a place in Denmark. And here you can see some of the pictures of them trying to do it. And so we increase the degree of complexity of the talk, of the subject that we're talking, that was quantum computer. And at the end, they use the quantum computer to solve a problem, but they also need to come with their own problem and show it to us. And this was the moment that they did the pitch of the problems to us, and we discussed a bit how we could improve and how what kind of problems they were trying to solve. So it was a 3-day camp with them. It was super nice, super cool to interact with them, and also to show this new technology, right, for young girls. Yes, so I will stop here.
Wonderful. Thank you,
Yes.
Heisa. And it's
You're
great
welcome.
with pictures too. There are already some discussions going on Discord about squeezed light. How does it compare to a standing wave, whether it's a superposition of standing waves?
Sorry, I'm trying to stop my sharing screen, but my Zoom.
I stopped it.
Thank you, Malu.
This is the end of the session. Thank you all very much. The team will stay on for a bit. So if you want, stay on as well, ask more questions, ask organizational questions. But this is the official end of the session and feel free to go. Then starting with a technical question. Heisa, can you share again, summarize what is squeezed light and how does it compare with standing waves?
Yes, so I will not compare directly with standing waves, but with coherent light. I think it's a bit easier. So let's think about the concept of coherent states of light. So if you think about a perfect laser, so laser is these photons, right? Coherent packets of photons. You have an amount of noise that will be always present there. And I will use the definition that this is what we call the vacuum noise, okay? And in experimental physics, we call this in general shock noise. So this noise will be always present. Does not matter how much you improve your system, it will be there. And way to go beyond this noise level is to use quantum states of light. And the squeezed states of light are states that if you can compress this noise below the noise of a coherent state. So if you could define this in what we call a phase diagram, the squeezed vacuum states are represented by a circle in this phase diagram. So they have equal noise around the quadratures. When you have squeezed states, you can compress one of the quadratures, as we call them, below this vacuum noise. And on the other hand, you have the expansion of the other one because of the Heisenberg principle. So this is the magic of squeezed states, right? We're operating in a noise level that is below the shock noise. And yeah, there are many ways that you can produce them. Yes, and I don't know if you have another question about it.
Yeah, we need to organize a separate session on that.
Yeah.
There are also questions about Q-bronze, Q-nickel, and deadlines. The deadline for Q-bronze is upcoming Friday, July 14th. There have been requests to postpone the deadline for Q-nickel. And we indeed understand that it's a very busy week for finishing Q-bronze. So yes, we have extended the deadline for Q-nickel until Monday, July 17th. So everyone also has the weekend to finalize the Q-nickel module. We will update the canvas soon. I hope that might make some people happy to obtain those certificates. What will we do the next days? Today, with David's keynote, David DiVincenzo keynote, you got a broad overview, and then we went really in depth for neutral atom quantum computing. You learned some of the basics, how the DiVincenzo criteria work for those. Also some very new topics, depending on your own background, that might have been more or less accessible. There is a quiz about neutral atom quantum computing today, where you can revise some of the DiVincenzo criteria for neutral atom quantum computing. Then tomorrow, we dive into simulating and optimization on a neutral atom quantum computer with Pedro Lopez from Quera. This will be an exciting bootcamp, and you can also obtain a separate certificate for this bootcamp offered by Quera. There is a question from Shreya Modi. The lectures are a little bit tough for me to understand as I don't have a physics background. Is there any way that I can increase my understanding of everything? I would like the whole team to chime in here for different input. One way is the mentoring sessions. For example, today, just 1 hour for the lecture, CQTech, our partner, Constantine Quantum Technologies, gave a lecture on the basics of quantum and quantum mechanics for quantum computing. So really, what is a qubit? What is superposition? What is a single qubit gate? What is a multi-qubit gate? And those are the concepts that will be really useful for Q-bronze and other modules. The hardware lectures, indeed, depending on how deep you go, it requires a lot of physics knowledge. And there, try to grasp the basics and how the DiVincenzo criteria are fulfilled with these quantum computers. And then pick your topic that you're interested in to go more deeply if you want. And then you can learn the more physics basics there. For example, atomic physics for neutral atom quantum computing, or more about superconducting circuits for superconducting quantum computing. Are there other team members who want to chime in here? The lecture by CQTech will also be uploaded on YouTube, yes. That was a really great session. Same for the software. There has been a mentoring session on introduction to Qiskit, introduction to Circ. Those will also be uploaded.
Maybe just a nice reminder, like that on Wednesday you will have the keynote from Ilana. That is not a hardware lecture, but will be about diversity, how to become a CEO. Yes, so I think it would be also nice to have a break of the hardware lecture, started from more open term, right? And after I want to go to superconducting quantum computing.
Great you highlight this, Heisa. Ilana Wisby is the CEO of Oxford Quantum Circuits, one of the superconducting quantum computing companies in the world. This will be an exciting keynote from her perspective on quantum computing, entrepreneurship, diversity. Feel free to ask questions in advance already that we can share with Ilana. And then that will also be the day of our first virtual lab tour in industry. And the rest of the week also software bootcamps, and then a dive into photonic quantum computing, including virtual lab tour. The remaining questions we will discuss on Discord. Thank you all very much for the session today with David DiVincenzo, with Jeff Thompson, and we will see each other tomorrow and be in touch on Discord in the meantime. Thank you all and have a great afternoon, evening, night, morning. What is the time at your place? See you tomorrow. Bye.